Moons have long been overshadowed by their parent planets in the grand narrative of the cosmos. But these celestial companions hold secrets as fascinating as the planets they orbit. From volcanic infernos to icy geysers, and from mysterious surface features to hidden oceans, these moons tell stories of dynamic evolution, extreme environments, and untapped potential for life. Join us as we journey into the forgotten and unique moons of our solar system and beyond, uncovering their peculiarities and the groundbreaking science that brings them into focus. Hyperion, the sponge moon. Hyperion, one of Saturn's outer moons, is a world that defies conventional expectations. Its irregular sponge-like appearance sets it apart from other moons, earning it the nickname the Sponge Moon. Hyperion's highly porous structure is unlike anything seen in the solar system, making it an object of great scientific curiosity. The moon's unique shape and surface are likely the result of its low density, which is much lower than that of solid ice. This porosity suggests that Hyperion is composed primarily of loosely packed ice and rock, with a structure full of voids and pockets. These characteristics mean that Hyperion absorbs impacts differently from denser moons, producing craters with unusual sharp-edged rims. The moon's surface also reflects very little light, adding to its enigmatic character. The spinning of Hyperion is another thing that experts don't understand. Hyperion's spin is not stable and predictable like most moons, which have steady, synchronous orbits. Because of their gravitational pull on Saturn and close moons like Titan, these bodies are not stable. Because of this, Hyperion twirls around in its circle, giving viewers a face that is always changing. Theories about how Hyperion formed say it might be a piece of a bigger body that was broken up in a collision a long time ago. The piece's odd form and low density support the idea that it is a splinter. The fact that it is porous could be due to internal heating and gas release in its early past. The honeycomb-like holes in its structure may have been left behind by these processes. Despite its distance and small size, Hyperion has been closely studied by NASA's Cassini spacecraft, which captured detailed images of its surface. These images revealed the moon's unique texture in vivid detail, showing craters filled with a mysterious dark material. This material, possibly organic in nature, hints at the complex chemistry occurring on Hyperion and raises questions about its interactions with Saturn's magnetosphere. The uniqueness of Hyperion makes us think about how moons form and change over time. There are a lot of different natural processes that make celestial bodies, as shown by its uneven spin, sponge-like surface, and low density. Hyperion is one of the most interesting things in the solar system, both aesthetically and scientifically. It continues to pique people's interest and shows how different environments can be even in the same world. Albiorix, Saturn, the volcanic outlier. As a member of the Gallic group of outer moons, Albiorix is a small moon with a strange shape that orbits Saturn. Albiorix is famous for having an odd reddish color, but new research suggests it may also have signs of cryovolcanism. This is a shocking possibility, given how far away it is and how cold it is there. Measuring about 32 kilometers, 20 miles in diameter, Albiorix's surface exhibits a reddish coloration, likely caused by the presence of organic compounds, or tholins, formed through the interaction of solar radiation with methane and other volatile materials. These compounds provide a clue to the moon's chemical composition and hint at dynamic processes occurring beneath its surface. The potential for volcanic activity on Albiorix arises from its irregular shape and surface features. Observations indicate the presence of linear fractures and lobate flows, which resemble features associated with cryovolcanism on other icy moons. These formations suggest that Albiorix may have experienced internal heating sufficient to drive the movement of subsurface materials. Tidal interactions with Saturn and other nearby moons may be the source of this internal heat. While these interactions are weaker than those experienced by closer moons like Enceladus, they could still generate enough friction to melt pockets of water ice mixed with ammonia, or methane. This slushy material could then erupt through surface fractures, creating the observed flow-like structures. The extraordinarily smooth sections of Albiorix stand out against its highly cratered surface and are one of the most interesting aspects of the planet. Where frozen material has resurfaced earlier topography, these smooth patches might be cryovolcanic deposits. They might also be the product of collisions that broke the surface of underlying ice, which then melted and refroze. Albiorix might have volcanic activity, which makes people wonder what part it plays in Saturn's moon system. Could Albiorix, along with other moons of Saturn that are formed by cryovolcanoes, add to Saturn's ring system? Even though the moon's faraway path makes this less possible, the fact that it could come back to the surface suggests a dynamic past that needs more research. Albiorix also challenges assumptions about the conditions required for cryovolcanism. Its small size and remote orbit suggest that even minor tidal forces, combined with radiogenic decay, can sustain internal activity in icy moons. This broadens the range of environments where volcanic processes might occur, with implications for other icy bodies in the outer solar system. Visiting Saturn's moons in the future may allow astronomers to better understand Albiorix and its mysterious characteristics. The surface structures might be either caused by cryovolcanism or caused by other geological processes. High-resolution imagery and spectroscopic research could assist determine which. Research of this kind may also help us better understand the evolution and history of Albiorix by revealing its surface and underlying layer compositions. Miranda, Uranus, the Frankenstein moon. Miranda, one of Uranus's tiniest moons, has a lot of strange natural traits that no one can explain. There are sharp edges between very different areas on the Frankenstein moon, which makes it look like its surface was put together from different terrains that don't go together. Miranda is one of the most interesting and mysterious moons in the solar system because of how strange it looks. Miranda's surface is a chaotic mosaic of ridges, grooves, cliffs, and cratered plains. Among its most striking features are the coronae, enormous oval-shaped regions of ridges and troughs that dominate the moon's landscape. These coronae are unlike anything seen elsewhere in the solar system and may have formed due to tectonic activity or upwelling of material from Miranda's interior. The boundaries of these coronae are sharply defined, suggesting that they were formed relatively recently in geological terms. Verona Rupes, the largest known cliff in the solar system, is one of Miranda's most well-known features. This sheer wall of ice rises an amazing 12 miles, 20 kilometers, above the ground below. Tectonic forces are thought to have pulled Miranda's rock apart, which is how it formed. Being on the moon would make it take longer to fall from the top of Verona Rupes. It would take you almost 12 minutes to get to the bottom. There are as many theories about how Miranda formed and changed over time as there are traits on its surface. One theory is that Miranda was broken by a huge impact and then put back together from the pieces that were left over. That would explain why it looks patchwork and why there are big differences between the areas. Another idea is that the internal warmth needed to power the geological processes that shaped Miranda's surface was caused by the tides from Uranus and its nearby moons. Furthermore, Miranda's surface is very rough. Its small size and low gravity make it unlikely that it has a busy core right now. However, in its early past, heat from tidal interactions with Uranus may have melted some of its icy core. This may have caused tectonic activity and the formation of the coronae. This time of action inside Miranda would have been short, and it would have stayed this way for billions of years. Miranda's unique characteristics were first revealed during the Voyager 2 flyby in 1986, which provided the only close-up images of the moon to date. These images showed not only the dramatic coronae and cliffs, but also evidence of ancient cratering, suggesting that some regions of Miranda's surface are far older than others. The sharp contrasts in age and terrain underscore the moon's complex history. By studying Miranda, We can learn a lot about the natural processes that can happen on small, icy moons. Its surface can be used as a natural classroom to learn about how celestial bodies are shaped by forces inside them, even ones that don't have a lot of energy. Miranda's Frankenstein-like look makes us think of how different the moons are in our solar system, and how their stories can go in a lot of different ways. Nereid, Neptune. The Wandering Moon. Nereid, one of Neptune's outer moons, is a mysterious celestial entity with a very erratic orbit, making it one of the most unique moons in the solar system. Since its discovery in 1949, Nereid, sometimes known as the Wandering Moon, has perplexed scientists with its erratic route and distant orbit. This intriguing moon provides insight into the dynamic dynamics that regulate Neptune's satellite system, as well as the larger processes of planetary development. Nereid's orbit is the most eccentric of any known moon, ranging from about 1.4 million kilometers, 870,000 miles, at its closest point to Neptune, to nearly 10 million kilometers, 6.2 million miles, at its farthest. This extreme variation suggests that Nereid may have been a captured object, possibly originating from the Kuiper belt or beyond. Its irregular orbit supports the theory that Nereid's position was disrupted by the arrival of Triton, Neptune's largest moon, which itself was likely a captured dwarf planet. The composition and surface features of Nereid remain largely unknown, as no spacecraft has flown close enough to capture detailed images. However, spectral observations suggest that Nereid's surface is composed of water ice mixed with organic compounds. Its surface reflects sunlight in a way that indicates significant weathering from cosmic radiation, hinting at a long and tumultuous history. Nereid's peculiar orbit presents significant obstacles in studying its development. Unlike other moons, which have relatively stable orbits throughout time, Nereid's course is extremely unpredictable, resulting in intricate gravitational interactions with Neptune and its neighboring moons. These encounters may have changed Nereid's orbit, bringing it closer to Neptune at specific stages in its history. Such alterations might explain the moon's current location and possible involvement in influencing the early dynamics of the Neptunian system. Theories about where Nereid came from and her past are closely linked to Neptune's purchase of Triton. When Neptune's pull caught Triton, its huge retrograde rotation probably messed up the paths of other moons. Some smaller moons may have been thrown out of the planet completely, while others, like Nereid, were thrown into orbits that were not straight. Nereid is a reminder of Neptune's violent past because of this chaotic time of rebuilding. Nereid's wandering nature also has implications for understanding the capture and retention of moons in the outer solar system. If Nereid is indeed a captured object, studying it could provide valuable insights into the processes that bring Kuiper belt objects or other distant bodies into orbit around giant planets. These processes are critical for understanding the formation and evolution of moon systems around gas giants like Neptune. Trips to Neptune might give us a better look at Nereid and its unique features. Detailed studies of its surface, composition, and orbital behavior could help us figure out where it came from and what part it plays in Neptune's complex system of moons. These kinds of projects could also look into the bigger effects of capturing moons and changing orbits on how planetary systems are formed. Mimas, Saturn, the Death Star moon. One of Saturn's closest moons, Mimas, is often compared to the Death Star from Star Wars because of its huge Herschel crater, which makes it look a lot like the imaginary space station. But Mimas is more than just a beautiful sight. It hides a lot of secrets and complexities below its icy surface, making people question the idea that it is just a frozen, lifeless world. The Herschel crater, which spans about 130 kilometers, 80 miles across, dominates Mimas's surface. This crater is nearly one-third the moon's diameter, a testament to the violent impact that formed it. The impact was so powerful that it likely came close to shattering Mimas entirely. Evidence of this near catastrophe can be seen in the extensive fractures and deformations on the moon's opposite side. which formed as shock waves from the impact traveled through its core. Mimas's density and surface composition suggest it is primarily made of water ice with a small, rocky core. Its heavily cratered surface indicates a long history of impacts, with Herschel crater being the most prominent. Despite this, recent findings from NASA's Cassini mission have raised questions about what lies beneath Mimas's icy shell. Subtle oscillations in its orbit, known as librations, suggest the possibility of a liquid or slushy interior, hinting at the presence of a subsurface ocean. It's strange that Mimas could have a secret ocean, since it's not very big and the tides don't heat it up very much. However, because it is so close to Saturn, it is affected by gravity forces that could create enough heat inside to keep water liquid below its cold surface. If this ocean is true, Mimas would join Europa and Enceladus as possible places for microbes to live. Mimas's orbit within Saturn's ring system also makes it an important player in shaping the rings. Its gravitational influence creates gaps, such as the Cassini division, and helps maintain the structure of the rings. The Moon's interactions with Saturn's magnetosphere further reveal the dynamic relationship between moons and their parent planets in the outer solar system. Mimas continues to astonish scientists with its hidden intricacies, despite its small size and seemingly simple look. Its putative subterranean ocean raises crucial issues regarding how liquid water might survive on tiny, icy worlds, broadening the spectrum of settings deemed livable. Future expeditions to Saturn's moons might reveal more solid answers, shining light on the mysteries hidden under Mimas's ice shell. Rhea's cryovolcanic mystery, Saturn, rings of ice and activity. The interesting and subtle case for possible cryovolcanic activity is made by Rhea, Saturn's second largest moon. Even though Rhea doesn't have the dramatic plumes of Enceladus or the clear geysers of Triton, there is proof that it may have been a cryovolcano in the past, leaving behind mysterious traits that show how active it was. Rhea stands out among the solar system's moons due to its distinctive weak ring structure. Anomalies in Saturn's magnetic field around Rhea were discovered by NASA's Cassini mission, which suggests that tiny particles are circling the Moon. The ice that formed Rhea's orbit may have been expelled during previous cryovolcanic eruptions, from whence these particles may have originated. The Moon's heavily cratered surface reflects a long history of impacts, but some regions show unusual features, such as smooth plains and subtle ridges, which could be remnants of cryovolcanic flows. These regions appear to have fewer craters, indicating they may have been resurfaced more recently than the surrounding terrain. Such resurfacing could have occurred as liquid water or a slushy mixture of ice and other volatiles erupted from the Moon's interior and froze upon reaching the surface. Rhea's composition provides further evidence for its potential cryovolcanism. Like many moons in the outer solar system, Rhea is primarily composed of water ice with a small fraction of rocky material. The presence of ammonia or other antifreeze compounds could lower the freezing point of water, allowing subsurface liquid reservoirs to exist even in the cold environment of Saturn's system. These reservoirs could have powered episodic cryovolcanic eruptions, shaping Rhea's surface over time. The mechanism driving Rhea's potential cryovolcanism likely stems from tidal heating, albeit less intense than on moons like Enceladus. Rhea's orbit around Saturn is relatively stable, but interactions with neighboring moons could generate enough internal friction to create localized heating. This heat may have been sufficient to melt pockets of ice within Rhea's crust, leading to periodic eruptions in the Moon's past. The oxygen and carbon dioxide that make up Rhea's thin exosphere also hold some clues. This extremely thin atmosphere, however, does point to weathering or outgassing from the Moon's interior that occurs continuously on the Moon's surface. This exosphere may have originated from cryovolcanic eruptions, which released volatile substances that were trapped in Rhea's weak gravitational field. Sending missions to Saturn might help us figure out what happened with Rhea's cryovolcanoes in the past. High-resolution images and spectroscopic analysis of its surface could show chemical signs of cryovolcanism, and gravitational studies could find strange things below the surface that could point to liquid reserves. More in-depth study of Rhea's faint rings might also reveal information about where they came from and how they might be connected to the Moon's past activities. Phobos, Mars, a moon spiraling toward doom. Phobos, Mars' bigger and closer moon, has a bleak fate. Phobos is slowly spiraling toward Mars owing to tidal forces, and it is on a collision path with its home planet, where it will either crash onto the surface or disintegrate into a ring of rubble. This imminent fate makes Phobos one of the solar system's most interesting and active moons, with a tail fashioned by gravitational forces, distinct geology, and a mystery origin. Phobos orbits Mars at an incredibly close distance, just 6,000 kilometers, 3,700 miles, above the planet's surface, closer than any other moon to its parent planet in the solar system. Its proximity to Mars subjects it to intense tidal forces that are slowly pulling it inward. Scientists estimate that in about 50 million years, Phobos will either crash into Mars or break apart into a ring of debris. This phenomenon highlights the delicate gravitational balance that governs moon-planet systems. Phobos is a small, irregularly shaped moon, just 27 kilometers, 17 miles across at its widest point. Its surface is covered with craters, grooves, and ridges, with the most prominent feature being Stickney crater, a massive impact scar that dominates one side of the moon. Stickney's formation likely sent shockwaves through Phobos, creating the grooves and fractures seen across its surface. The grooves on Phobos have puzzled scientists for decades. Initially thought to be impact-related, recent studies suggest they may be the result of tidal stresses caused by Mars's gravity. These stresses are slowly deforming the moon, contributing to its eventual demise. Alternatively, some researchers believe the grooves could have formed from material ejected during the Stickney impact, or as a result of interactions with space debris. Phobos's makeup gives us hints about where it came from. Like C-type asteroids, it is thought to be made up of carbon-rich rock and water ice. Because of this resemblance, some people think that Phobos might be an asteroid that was caught, but the fact that its orbit is almost circular makes this idea less likely. Another idea is that Phobos formed from the leftovers of a big impact on Mars, which is similar to how Earth's moon is thought to have formed. Phobos's proximity to Mars makes it a prime target for exploration. Its low gravity and proximity to the planet make it an ideal staging point for future missions to Mars. Space agencies have proposed sample return missions and robotic landers to study Phobos's surface, composition, and evolution. These missions could help answer questions about the moon's origin and provide valuable insights into the processes shaping small bodies in the solar system. The fate of Phobos is a stark warning of how much celestial systems are dynamic and always changing. Even though it will be destroyed in the end, the processes that are sending it slowly toward Mars are a unique chance to learn about how tides work, how orbits change over time, and the forces that shape planets and moons. Mars, the frozen volcanic giants. Mars, the red planet, is home to some of the largest volcanic structures in the solar system. These colossal formations, now silent and frozen, provide a glimpse into the planet's tumultuous geological past. The towering Olympus Mons, vast lava plains, and mysterious volcanic ridges showcase a world once dominated by volcanic activity. At the forefront of Martian volcanism is Olympus Mons, the tallest volcano in the solar system, standing nearly 22 kilometers, 13.6 miles high. Olympus Mons dwarfs Mount Everest, stretching wide with a diameter of about 600 kilometers, 370 miles. This shield volcano formed over millions of years as repeated eruptions of basaltic lava created layer upon layer of rock. Its massive size is attributed to Mars's low surface gravity and the lack of tectonic plate movement, which allowed the volcano to remain stationary over a magma source. Another standout feature is Tharsis Rise, a volcanic plateau spanning over 5,000 kilometers, 3,100 miles. This region hosts three giant shield volcanoes, Ascraeus Mons, Pavonis Mons, and Arsia Mons, all of which are only slightly smaller than Olympus Mons. These volcanoes, along with the surrounding fissures and rift valleys, indicate that Tharsis Rise was once a center of intense volcanic and tectonic activity. The region's formation likely played a major role in shaping the planet's crust and atmosphere. Beyond the Tharsis region lies Elysium Planitia, another volcanic hotspot featuring Elysium Mons and Albor Tholus. These features suggest that Mars had multiple centers of volcanic activity, each contributing to the reshaping of the planet's surface. The extensive lava flows and plains surrounding these volcanoes hint at eruptions that spanned millions of years, flooding large areas with molten rock. The history of Mars volcanoes is closely linked to the history of its atmosphere. In the early days of the volcano, huge amounts of gases like carbon dioxide, water vapor, and sulfur dioxide were released during outbursts. It's likely that these gases helped make the atmosphere thicker, which let flowing water stay on the surface. Mars changed into the cold, dry world we see today when the volcanoes stopped erupting. The atmosphere also got thinner. The possible connection between Martian volcanism and current activity is one of the most fascinating features of this phenomenon. Research has shown that some areas, including Cerberus fossae, have seen recent volcanic eruptions, maybe within the last several million years. Satellite photos show what appear to be new deposits and dark lines, which might mean that Martian volcanic activity is still going strong. The volcanic activity on Mars also raises the possibility of habitable environments. Subsurface heat generated by volcanic processes could create pockets of liquid water, providing potential habitats for microbial life. Features like lava tubes and volcanic caves could shield organisms from harsh surface conditions, preserving niches where life might persist. Mars volcanism is a mystery that scientists are trying to solve. In order to learn more about Earth's geologic past, the Perseverance rover is studying old volcanic rocks. Future missions could focus on studying particular volcanic areas. The composition and history of Mars can be better understood via the study of meteorites, many of which come from volcanic areas. Iapetus, Saturn, the two-toned mystery. Iapetus, its surface is very different from one side to the other. One half is bright and shiny, covered in water ice, and the other half is dark and covered in a material that is rich in biological matter. Iapetus is called the yin-yang moon because it has two different colors on its surface. Scientists are very interested in it. The origin of Iapetus's two-toned surface remains a topic of debate. One leading theory suggests that the dark material comes from Phoebe, another of Saturn's moons. As Phoebe orbits Saturn, it sheds a fine layer of dust that gradually accumulates on Iapetus's leading hemisphere, creating the dark region known as Cassini Regio. This hypothesis is supported by observations showing that Iapetus's orbit crosses the debris trail of Phoebe, allowing particles to coat its surface over time. Another idea holds that Iapetus's dark matter is the consequence of internal activities. Heat created during the moon's early history might have forced volatile substances like water ice to move from the warmer, sunny side to the cooler, shaded portions. This would leave behind black organic remains, resulting in the sharp contrast seen today. This phenomenon, known as thermal segregation, might explain the stark contrast between the dark and light hemispheres. Iapetus has beautiful colors and an equatorial line that is not found anywhere else in the solar system. This ridge goes around almost the whole moon and rises up to 20 kilometers, 12 miles, above the nearby land in some places. There are still a lot of ideas about where this ridge came from, but some of them involve an old ring system that fell onto Iapetus's surface or tectonic action inside the crater when it was first formed. Mysterious things about Iapetus include its slow spin. Iapetus takes more than 79 days to make one full turn, while most moons are tidally locked to their parent planets. It is different from other moons in the system because it spins slowly and is far from Saturn. This may have caused its strange surface traits, and internal structure. The composition of Iapetus provides additional clues to its history. The bright hemisphere is composed primarily of water ice, while the dark hemisphere contains carbon-rich compounds and possible traces of ammonia. These materials suggest that Iapetus formed from a mix of icy and rocky material, similar to other moons in the outer solar system. But its unique environmental conditions have shaped it into a world unlike any other. With its detailed pictures of Iapetus's surface and readings of its composition, the Cassini probe made it much easier to study. Scientists have used these facts to improve their models of how the moon formed and changed over time. But there are still a lot of questions that need to be answered. Deimos, Mars, the silent companion. Deimos, the smaller and more distant of Mars' two moons, often lives in the shadow of its larger sibling, Phobos. While Phobos garners attention for its doomed spiral toward Mars, Deimos quietly maintains its stable, smooth orbit. This silent companion offers a stark contrast to its more chaotic counterpart, yet it holds its own mysteries and potential for scientific exploration. Deimos is an irregularly shaped moon, measuring only about 15 kilometers, 9 miles, across at its widest point. Its surface is covered with a layer of fine regolith, which gives it a smoother appearance compared to Phobos. Unlike Phobos, which features prominent grooves and fractures, Deimos's surface is relatively uniform, with fewer large craters. The largest crater on Deimos, named Voltaire, is a modest 3 kilometers, 1.8 miles in diameter, emphasizing the moon's calm and unremarkable exterior. Deimos's smoothness and lack of surface features raise questions about its origin and evolution. One possibility is that Deimos, like Phobos, is a captured asteroid from the early solar system. Its composition, rich in carbonaceous material, supports this hypothesis. However, its nearly circular and equatorial orbit around Mars challenges the idea of an asteroid capture, suggesting that it may have formed from debris left over from an ancient impact on Mars. The orbital dynamics of Deimos set it apart from Phobos. Deimos orbits Mars at a distance of approximately 23,460 kilometers, 14,580 miles, far beyond the planet's synchronous orbit. This means that Deimos slowly drifts away from Mars over time, unlike Phobos, which is spiraling inward. Its distant and stable orbit also means it experiences less tidal stress, contributing to its smoother surface and lack of significant geological activity. Because Deimos is so small and has low gravity, it is hard to explore. It doesn't have much gravity, so something thrown at it with some force could get away from the surface. Even with these problems, Deimos has been suggested as a possible first stop for future human trips to Mars. Its safe orbit and low gravity make it a great place to set up a staging area or fuel store for trips to the surface of Mars. Even though Deimos doesn't have much natural action, that doesn't mean it isn't useful for science. Its surface regolith has probably not been touched in billions of years, so it could hold useful information about how the solar wind interacts with it and how much radiation it is exposed to. By looking at these things, we might learn more about the early solar system and Mars's past. Methone, Saturn, the egg moon. One of Saturn's tiniest moons, Methone, is often forgotten in favor of its bigger neighbors. But this tiny celestial body, which is known as the egg moon, is different from almost all the other moons in the solar system because its surface is so smooth. The diameter of Methone is only 3 kilometers, 1.9 miles, making it one of the tiniest moons that has ever been seen in great detail. However, its unique features make it an interesting object to study. Methone is unique because it doesn't have any holes, lines, or grooves. Other small moons have rough surfaces from impacts, but Methone's is smooth and even, like an egg that has been cleaned. It is strange that Methone is so smooth, since its small size and weak gravity should make it very easy to hit something. One possible reason is that Methone's surface is made up of a strange mix of fine-grained icy material that moves around like a fluid over geological ages, covering up evidence of past impacts. Charged particles from Saturn's atmosphere contact with the Moon's surface in a process called electrostatic lofting, which gives methane its smooth surface. Small bits of ice and dust may move across methane because of this interaction, filling in holes and making the surface look smooth. People have seen this happen on other small moons and icy bodies, but methane is one of the most dramatic cases. Methane's orbit is another fascinating feature of the event. It is one of many moons that circle Saturn between the bigger moons Mimas and Enceladus. Methane's location is maintained by an unusual gravitational interaction with Saturn and the adjacent moon, Mimas, which results in a phenomenon known as mean motion resonance. This resonance stabilizes methane's orbit and may affect its surface properties by restricting its exposure to collisions. Despite its small size, methane plays a role in shaping its local environment. Along with its neighboring moons Pallene and Anthe, methane contributes to a faint ring of material orbiting Saturn. These moons likely shed tiny particles of ice and dust, which are then distributed into a diffuse ring by Saturn's gravity and magnetosphere. Studying these interactions provides insights into the complex relationships between moons and their parent planets. Methane was first observed in detail by NASA's Cassini spacecraft, which captured high-resolution images of its surface and measured its orbit. These observations revealed not only methane's unique smoothness, but also its unusual egg-like shape, which is slightly elongated due to tidal forces from Saturn. Hippocamp, Neptune, the tiny latecomer. Hippocamp, the smallest and most recently discovered moon of Neptune, is a celestial oddity that defies traditional expectations for planetary satellites. With a diameter of just 34 kilometers, 21 miles, Hippocamp is a faint and elusive moon, yet its origin and current position provide critical clues to the history of Neptune's dynamic satellite system. Discovered in 2013 using the Hubble Space Telescope, Hippocamp has quickly become a subject of intrigue for astronomers. The closeness of Hippocamp to Proteus, the much bigger moon, is one of the most intriguing features of the planet. These two moons are the closest to each other in Neptune's system, with an orbital separation of only 12,000 kilometers, 7,500 miles. Given how near Proteus is, one wonders how Hippocamp escaped being thrown to the ground or crushed by his massive gravity. According to astronomers, Hippocamp might be a piece of Proteus that was formed long ago in a tremendous collision. Perhaps Hippocamp's material originated in Proteus's massive impact basin, which is located on the cratered but otherwise flat surface of the planet. Hippocamp's orbit around Neptune is nearly circular and lies in the same plane as Neptune's equatorial region. This suggests a relatively stable orbit despite its close proximity to Proteus. The small moon's position and orbital characteristics provide valuable insights into the aftermath of catastrophic events, such as collisions and fragmentations, and how debris can coalesce into stable bodies over time. The composition of Hippocamp remains unknown, as its faintness and small size make it challenging to study in detail. However, like other moons in the Neptunian system, it is likely composed of water ice and rocky material. Its surface, shaped by billions of years of micrometeoroid impacts and exposure to Neptune's magnetosphere, may hold important clues about the environment in the outer solar system. The development of better methods of observation also contributed to Hippocamp's discovery. In a focused hunt for minor moons in the Neptunian system, data from the Hubble Space Telescope uncovered it. Due to its small size, the moon's picture processing and analysis were extremely laborious, demonstrating the difficulties of discovering such tiny objects in other planetary systems. Hippocamp's finding highlights the need for further funding for large telescopes and cutting-edge imaging technology, so that we may continue to learn about the solar system's outer regions. Being one of the newest moons of Neptune, Hippocamp is very important for learning about how the planet's satellite system changes over time. The fact that it exists goes against the common belief that smaller moons are quickly killed or thrown out of systems where bigger bodies are dominant. Instead, Hippos Camp shows how the remains of violent crashes can survive and even grow in the right conditions. Helene, Saturn, a Trojan moon. Helene is a small icy moon of Saturn that stands out because it is a Trojan moon, because it lies in one of the so-called Lagrangian points along the path of another moon. Helene and Dione, Saturn's much bigger moon, share the same orbit. Helene lives at the L4 Lagrangian point, which is a gravitationally stable spot about 60 degrees ahead of Dione, as they both circle Saturn. This unusual orbital arrangement shows how dynamically complex Saturn's system is, since even small moons can move in ways that go against what we usually think about how satellites move. Discovered in 1980 via images from the Voyager 1 spacecraft, Helene measures around 36 kilometers, 22 miles, in diameter. Its surface is composed primarily of water ice, similar to many of Saturn's other small moons, though Helene stands out for its relatively bright appearance. Observations from the Cassini mission revealed a surface that bears features such as gentle slopes, shallow depressions, and subtle color variations. The presence of smooth regions indicates that Helene may have experienced some geological processes, possibly minor landslides or slow-moving ice flows, that partially reshaped its terrain over time. The way Lagrangian points work is one of the things that makes Helene's role as a Trojan moon so interesting. These points are caused by the gravitational pull of a planet, Saturn, and a large moon, Dione. They make areas in the gravity field that are stable or almost stable. There is an area called the L4 point in Helene's orbit where the combined gravitational pull of Saturn and Dione, along with the system's circular motion, keep Helene in place, always a certain angle ahead of Dione. This arrangement grants Helene a unique vantage within Saturn's system. While it orbits at roughly the same distance from Saturn as Dione does, the Trojan relationship spares it from direct tidal encounters that might otherwise yank it off course. Such stability is not infallible. Minor perturbations from other moons and ring material can shift Helene's exact position, but the gravitational well at L4 effectively corrals the moon. Over millions of years, Helene has drifted somewhat within that region, but shows no sign of escaping it entirely. Surface traits give us more information about Helene's past. Helene has some smaller impact craters, but not many big ones. This suggests that any violent crashes it may have had in the past may not have been very bad, or that craters fill in over time due to geological processes. In close-up pictures taken by Cassini, some parts of Helene's surface show bright streaks. These may be ice grains that have slid downhill or been moved around by micrometeorites. Even though they are slow, these processes can renew the surface, making it brighter and less cratered than the surface of a body that is just as old but doesn't change geologically. Helene's brightness and unusual location in Dione's orbital path make it an object of keen scientific interest. Understanding how Helene reached the L4 point and remains there can shed light on broader questions about satellite capture, orbital evolution, and the dynamic interplay of gravitational forces within planetary systems. In some ways, Helene's orbit mirrors that of Trojan asteroids associated with planets like Jupiter or Mars, reinforcing the idea that such arrangements can occur across the solar system, not just with large bodies, but also with small icy moons. As scientists continue to look at Cassini's data, Helene's geography and path are a key part of figuring out the family tree of Saturn's moons. Its role as a Trojan moon shows how beautiful the outer solar system's gravitational pull is. Even in the midst of giants like Saturn and Dione, small, icy friends can find safe places to live. Tethys, Saturn, the ice moon with a giant canyon. The icy world of Tethys, one of Saturn's major moons, is ruled by two huge features, the Ithaca Chasma and the Odysseus crater. These impressive landmarks tell us a lot about Tethys's past and the changing forces that shaped its surface. Even though Titan and Enceladus are more well known as moons of Saturn, Tethys is still a great place to learn about the nature of icy objects in the outer solar system. The most prominent feature on Tethys is Ithaca Chasma. a colossal canyon system stretching over 2,000 kilometers, 1,200 miles, and covering nearly 3/4 of the Moon's circumference. This canyon, up to 100 kilometers, 62 miles, wide and 4 kilometers, 2.5 miles deep in places, is believed to have formed during a period of significant internal activity. One leading theory suggests that Ithaca Chasma resulted from the cooling and freezing of Tethys's subsurface ocean in its early history. As the liquid layer solidified, it expanded, causing the Moon's icy crust to crack and form the chasm. The Odysseus crater, located on Tethys's surface, is another key feature that speaks to the Moon's violent past. This massive impact basin spans nearly 450 kilometers, 280 miles, making it one of the largest craters relative to the size of its host moon in the solar system. Despite its immense size, the crater appears relatively shallow, likely due to the low density of Tethys's icy surface, which flows and deforms over time. The impact that created Odysseus was powerful enough to fracture Tethys's crust, potentially contributing to the formation of Ithaca Chasma. Tethys is composed primarily of water ice, with a small fraction of rock and other materials. Its low density and bright reflective surface indicate a high concentration of ice, making it one of the most visually striking moons in the Saturnian system. The icy composition also plays a significant role in shaping Tethys's surface features, as ice behaves differently from rock under the stress of impacts and internal forces. Tethys doesn't have any major geological action going on right now, which suggests that its core has cooled and solidified, making it geologically quiet. But in the beginning, the Moon may have had enough energy from tidal interactions with Saturn and nearby moons to keep an ocean below the surface. These reactions, along with radiogenic warmth, may have caused the internal activity that made features like Ithaca Chasma possible. Despite its icy exterior, Tethys plays a role in Saturn's magnetosphere and ring system. As Tethys orbits Saturn, it interacts with the planet's magnetic field and contributes particles to the E-ring, a diffuse ring of icy material. This interaction highlights the dynamic relationship between Saturn and its moons, where even relatively inactive bodies like Tethys can influence the surrounding environment. NASA's Cassini probe carefully studied Tethys by taking detailed pictures of its surface and studying what it is made of. These studies have taught us a lot about the Moon's rocks and the processes that made it. But there are still a lot of questions about Tethys's early history and the possibility of action below the surface. Rhea, Saturn, the moon with a faint ring. Rhea, the second largest moon of Saturn, is a world of ice and rock with a serene appearance. However, beneath its calm exterior lies a unique mystery. Rhea may be the only moon in the solar system surrounded by a faint ring system. This unexpected feature, coupled with its heavily cratered surface and intriguing interior, makes Rhea a standout among Saturn's many satellites. The possibility of rings around Rhea was first suggested during the Cassini mission, when instruments detected subtle changes in Saturn's magnetic field near the Moon. These anomalies could only be explained by the presence of small particles orbiting Rhea, forming a thin diffuse ring system. If confirmed, this would make Rhea the only known moon with its own ring, a distinction that has sparked significant interest in its formation and dynamics. Rhea's rings, if they exist, are likely composed of icy particles and debris. One theory suggests that the material originates from meteoroid impacts on Rhea's surface, which eject small fragments into orbit. Over time, these particles could form a stable ring system, held in place by Rhea's gravity. Another possibility is that the rings are remnants of a destroyed moonlet or comet that once orbited Rhea. The surface of Rhea is full of marks from strikes that happened billions of years ago. Its highly cratered surface shows that it has been hit by many things over a long time. Some of the craters show signs of ice flows and tectonic action that happened a long time ago. In its early past, Rhea may have been geologically active, with heating inside and tectonic forces forming its surface. Another interesting aspect of Rhea is its composition. The Moon is mostly composed of water ice, with a density that suggests a modest rocky core. Rhea's dazzling shiny appearance is due to her ice composition, which is comparable to that of other major Saturnian moons. Variations in surface composition, such as black streaks of material around craters, may indicate complicated processes that revealed deeper layers of the moon's crust. The potential for a faint ring system around Rhea raises questions about the interactions between moons and their surrounding environments. If Rhea's rings are confirmed, they could offer valuable insights into the processes that shape moon ring systems and the ways in which moons influence their parent planet's magnetosphere and rings. Rhea is a very active planet in Saturn's system, even though it looks calm. The moon's possible rings and highly cratered surface show how it interacts with the world around it. Its icy composition and old tectonic features tell us about its interior and early past. As a one-of-a-kind moon that might have a ring system, Rhea continues to push our ideas about how different and complicated the bodies in the outer solar system are. Amalthea, Jupiter, the colorful inner moon. Amalthea is one of a kind in Jupiter's system of moons. Its color is red, and its shape isn't straight. Even though it's not very big, this moon has a big impact on the area around Jupiter. It adds material to Jupiter's strong radiation belts and changes the planet's faint ring system. A notable aspect of Amalthea is its unusual hue. The volcanic powerhouse of Jupiter, Io, is likely responsible for its crimson surface, along with other volcanic elements. As it approaches Jupiter in its orbit, these particles settle upon Amalthea, giving it a splotchy, multicolored appearance. Amalthea displays vivid green spots next to the red areas. These might be the result of exposed water ice interacting with non-ice substances. The moon's irregular shape reflects its history of formation and evolution. Measuring about 250 kilometers, 155 miles at its longest dimension, Amalthea is not massive enough for gravity to pull it into a spherical shape. Instead, it retains a lumpy, elongated form, suggesting that it has remained relatively untouched by significant geological processes. Amalthea's heavily cratered surface further supports this idea, with craters like Pan and Gea indicating a long history of impacts. A further aspect that makes Amalthea unique is its rotation. It is one of Jupiter's nearest moons, only 181,000 kilometers, 112,000 miles, from the planet's center. It is in the strong radiation belts that Jupiter's strong magnetic field creates. Because of its closeness, Amalthea is exposed to very high amounts of radiation, which could change the chemistry and physical qualities of its surface. Even though things are bad, Amalthea stays safe in its path because Jupiter's gravity is so strong. Maintaining Jupiter's thin gossamer rings is one of Amalthea's most fascinating contributions to the Jupiter system. Many of the small dust and ice particles that make up these rings are thought to have originated from the moon Amalthea and other surrounding moons. Meteoroids collide with Amalthea's surface, sending material splattering into space where it eventually forms the fragile rings. The procedure emphasizes how the rings and moons of Jupiter are interdependent on one another. Amalthea's low density and composition suggest that it is primarily made of water ice with a smaller proportion of rocky material. This composition is unusual for a moon so close to a giant planet, as inner moons are typically denser and more rock-rich. Amalthea's icy makeup raises questions about its origin, with some scientists proposing that it formed further out in the solar system and was later captured by Jupiter's gravity. There are still numerous mysteries surrounding Amalthea's composition and history, despite the fact that it has been thoroughly explored by spacecraft and telescopes, such as the Galileo expedition. Amalthea and its function in Jupiter's dynamic system may be better studied by future Jupiter missions like JUICE, Jupiter Icy Moons Explorer, which is operated by the European Space Agency. The uneven form, multicolored surface, and ring components of Amalthea make it an intriguing topic of study. Being one of Jupiter's nearest moons, it sheds light on the harsh conditions surrounding massive planets and the complex processes that mold their satellite systems. Thebe, Jupiter, the outermost inner satellite. Thebe is one of Jupiter's closest moons. It stands out because it is the largest member of Jupiter's Galilean ring of inner satellites. Thebe, along with Metis, Adrastea, and Amalthea, orbits close to Jupiter and is hit by the planet's strong radiation belts. Even though it is in a hostile environment and is only about 100 kilometers, 62 miles, across at its largest point, Thebe is an important part of Jupiter's dynamic system. It adds to the faint ring material and connects with the Jovian magnetosphere. Discovered in 1979 by the Voyager 1 spacecraft, Thebe orbits roughly 222,000 kilometers, 138,000 miles, from Jupiter's center, placing it just outside Amalthea's path. Its position makes it vulnerable to the powerful radiation emanating from Jupiter's magnetosphere, a region teeming with charged particles accelerated by the planet's colossal magnetic field. Though Thebe lacks the volcanic activity that defines nearby Io or the unique coloration of Amalthea, it stands out for other reasons, not least of which is its heavily cratered surface. One particularly large impact site, sometimes referred to as Zethus crater, dominates Thebe's hemisphere, revealing a history of bombardment by micrometeoroids and larger debris over billions of years. Like many small Jovian moons, Thebe likely consists primarily of water ice and rocky material. This mixture, along with its irregular shape, suggests a porous structure where impacts easily loft debris into space. Indeed, one of Thebe's defining contributions to Jupiter's system is dust production. Material blasted off its surface by collisions drifts outwards, eventually forming part of the Thebe-Gossamer ring, an extremely tenuous ring that orbits in the same region as the Moon. This dusty halo is faint, best observed using sensitive instruments that track forward-scattered sunlight. Nonetheless, Thebe's role in maintaining this ring underscores the complex interplay between the giant planet's moons and ring particles. Thebe's fate is also affected by exchanges in orbit. It goes around Jupiter once every 16 hours, while Jupiter turns once every 10 hours. The difference in angular speeds causes friction-like effects in the plasma-filled magnetosphere, which causes small changes in Thebe's orbital elements over long periods of time. Thebe's gravity helps keep the dust in the area spread out, but it is too small to make a big hole in Jupiter's rings like Pan or Daphnis could in Saturn's rings. NASA's Galileo probe revealed that Thebe adds a steady stream of material to the ring. This material replaces dust that is lost in Jupiter's atmosphere or pushed out by the sun's radiation. Surface features on Thebe affirm its active bombardment history. In contrast to the smoother appearances on small moons near Saturn, like Methone or Atlas, Thebe's rugged topography bristles with craters, pits, and ridges. Each impact reveals a new layer of ice or rock, giving researchers glimpses of the moon's internal composition. Over eons, the accumulation of debris around Thebe, combined with varying radiation intensities from Jupiter, ensures that its surface undergoes constant low-level modification, though without the dramatic changes seen on volcanically active worlds. If you look at the big picture, little satellites like Thebe may make a big impact on the environment around a gas giant. Planets, their magnetospheres, and the countless minor moons orbiting them form an intricate web, which Thebe's experiences illuminate, from contributing dust to Jupiter's delicate rings to reflecting the relentless barrage of charged particles. Investigating these processes enhances our understanding of the evolution of ring-moon systems, demonstrating that even lesser-known bodies such as Thebe deserve our consideration in deciphering the mysteries surrounding Jupiter and its neighbors. Carpo, Jupiter, the lone irregular satellite. Being one of Jupiter's outer irregular moons, Carpo is tiny, has an erratic trajectory, and is located far from any of the planet's other satellites. This enigmatic rock, which was found in 2003 and just a few kilometers across, subtly draws attention to the dynamical complexity and variety of the Jovian system. A steeply inclined eccentric track that suggests a potential capture or disruptive previous event characterizes Carpo's orbit, in contrast to the normal Moon's almost equatorial prograde orbits around Jupiter. The irregular satellites of Jupiter, dozens in number, generally fall into orbital families, often sharing similar inclinations or eccentricities that suggest a common origin. Carpo, however, has emerged as something of an outlier. It orbits in a prograde direction, unlike some of the larger irregular moons, which orbit retrograde. Its semi-major axis, inclination and eccentricity are sufficiently distinct that it appears to wander alone, separated from the known orbital groups. This solitary nature has led astronomers to debate whether Carpo was once part of a larger family but drifted over time due to gravitational perturbations, or if it formed independently and was captured long after Jupiter's major satellite systems coalesced. Carpo was only recently found, but the information we have so far suggests that it probably comes from a part of the solar system beyond Jupiter, maybe the outer asteroid belt, or even the area near the Trojans. If it was captured, it would have had to be a very complicated event involving Jupiter's strong gravity, the object's speed, and either a third body or a frictional mechanism to lower the energy of the approach. Scientists are still studying these capture processes in many different planetary systems because they can explain how giant planets build up large rings of irregular satellites over billions of years. Because of its distance from Jupiter and small size, Carpo is difficult to observe in detail. Most information comes from tracking its orbit through telescopic surveys that measure minute changes in position against background stars. These surveys indicate that Carpo's orbit can be perturbed by more massive moons or the cumulative gravitational influence of the Sun and Jupiter over extended periods. Such ongoing shifts may one day push Carpo into a collision course with a larger satellite, or conversely eject it from Jupiter's sphere of influence to become a wandering object in heliocentric orbit. Whether Carpo's ultimate fate is to remain a lonely moon, or embark on a new trajectory, is an unfolding question in the study of Jupiter's outer satellites. In addition to being interesting, Carpo shows us how random satellite systems are put together. These processes are controlled by gravity, collisions, and the movement of orbits over very long periods of time. Looking at Carpo's path and makeup could help us figure out how many small things Jupiter has caught since the beginning of the solar system. If scientists or spacecraft in the future are able to get a better idea of Carpo's surface or makeup, they might find spectral clues that connect it to a certain area of origin. This would help us understand how matter moves through the early solar nebula. Oberon, Uranus, the ancient moon. Oberon is the furthest big moon of Uranus. It is a strange, shadowy globe with craters and frozen deposits that suggest a complicated past. Oberon is one of the solar system's most understudied moons despite its significance as Uranus's second largest moon, and a major component in the planet's satellite system. Its fascinating geological characteristics and old surface provide a rare window into the Uranian system's early past. Oberon's surface is heavily cratered, indicating that it has remained geologically inactive for billions of years. Many of these craters are surrounded by bright rays of ejecta, suggesting that they are relatively fresh in geological terms. One of the largest craters, Hamlet, spans over 200 kilometers, 124 miles, in diameter, and features a central peak typical of large impact basins. These craters serve as a record of the heavy bombardment that characterized the early solar system. Oberon appears old, yet there are indications of geological activity from the past that are more subtle. There is a black substance on the floors of a number of craters, which could represent organic chemical deposits combined with water ice. Furthermore, linear cracks and scarps may be seen in certain areas, which could indicate that the moon was subjected to internal stress and tectonic activity long ago. Radiogenic heating or tidal pressures may have caused this activity in Oberon's early past. Oberon's composition is thought to be a mix of water ice and rock, with a density suggesting that roughly half of its mass is rock. This composition places it in line with other large moons in the outer solar system, such as Titan and Callisto. The presence of water ice raises the possibility of a subsurface layer of liquid water, though there is currently no direct evidence for this. The possibility of cryovolcanic deposits is one among the most interesting things about Oberon. Some of the black stuff on the Moon may represent cryovolcanic eruption leftovers, according to observations. If this is correct, it would mean that Oberon's interior was formerly active and may have supported underground slush or liquid water reservoirs. The Moon's surface may now have its own distinct chemical environment, thanks to material that was carried to it from the Moon's core during these eruptions. Oberon's location in the Uranian system also provides insights into its history. As the outermost of Uranus's major moons, Oberon is less affected by tidal forces compared to its closer counterparts, such as Miranda and Ariel. This relative isolation may have allowed Oberon to retain its ancient surface features, preserving a record of the early solar system's impact history. Oberon was first observed in detail by the Voyager 2 spacecraft during its flyby of Uranus in 1986. Although the images provided valuable information about the Moon's surface, they were limited by the technology of the time. Since then, no missions have returned to Uranus, leaving many questions about Oberon's geology and composition unanswered. Because of better imaging and spectroscopic tools on future trips to Uranus, we might learn more about Oberon's surface traits and any possible action going on inside the planet. These kinds of studies would tell us a lot about how icy moons form in the outer solar system and how impacts from the past have affected the development of planets. Charon, Pluto, the partner moon. As a full member of one of the solar system's most unusual planetary systems, Pluto's biggest moon, Charon stands apart. Charon is the biggest moon in relation to its home planet in our solar system, with a diameter of 1,212 kilometers, 753 miles. This makes it roughly half the size of Pluto. Pluto and Charon are in a binary system because of their very small size ratio. Pluto's surface is not the barycenter. Charon plays a pivotal role in Pluto's narrative because of the dynamic interaction that determines the behavior and evolution of both planets. Discovered in 1978, Charon remained a mysterious object until NASA's New Horizons mission flew past the Pluto system in 2015. The spacecraft revealed a world of surprising complexity, with a surface marked by vast canyons, mountain ranges, and smooth plains. Unlike Pluto, whose surface is dominated by nitrogen and methane ice, Charon's surface is primarily water ice, giving it a distinct appearance and composition. The crimson cap near Charon's north pole, which is colloquially known as Mordor Macula, is one of the most noticeable characteristics of the planet. Tholins, complex organic compounds produced by the interaction of UV light with methane, are believed to make up this dark, reddish area. It is quite probable that the methane leaves Pluto's atmosphere and is subsequently trapped by Charon's gravity. When methane is dumped onto Charon's surface, it freezes and goes through chemical changes, turning it into the crimson substance known as Mordor Macula. Charon's surface also features a massive canyon system that stretches for over 1,000 kilometers, 620 miles, longer than the Grand Canyon on Earth. This canyon, part of a network of tectonic features, suggests that Charon underwent significant geological activity in the past. The presence of smooth plains, such as Vulcan Planitia, indicates areas of resurfacing, possibly caused by cryovolcanism or the movement of subsurface material. The geological activity on Charon is thought to be linked to its internal structure and history. Early in its formation, Charon may have harbored a subsurface ocean of liquid water. As the moon cooled, the freezing of this ocean would have caused the surface to expand and crack, creating the tectonic features observed today. The presence of ammonia hydrates on Charon's surface supports the idea of past cryovolcanic activity, as ammonia acts as an antifreeze, lowering the freezing point of water and allowing it to remain liquid at lower temperatures. As a result of their tight connection, Charon and Pluto have a tidal locking phenomenon, which causes them to always present the same face to one another. Their orbits have been maintained, and the unusual dynamics of the Pluto-Charon system have been enhanced by their synchronous rotation. Styx, Nix, Kerberos, and Hydra, 4 of Pluto's smaller moons, form a complicated and resonant dance in their orbits, which is impacted by the binary structure of this system. Research on Charon sheds light on the mechanisms that form cold planets outside our solar system. Due to its distinct makeup, geological past, and ever-changing connection to Pluto, it is an important target for further investigation. Our knowledge of this intriguing moon and its place in the Pluto system may be greatly enhanced by missions that could do more thorough surface mapping, composition analysis, and exploration of possible subsurface structures on Charon. Dactyl, the first asteroid moon. Dactyl, the small asteroid that lives with Ida, is an important part of the history of space travel because it was the first known satellite of an asteroid. This discovery, made by NASA's Galileo probe in 1993, changed the way we think about small body dynamics by showing that even asteroids, which were once thought to be wandering objects, could have their own satellites. The discovery of Dactyl around Ida led to a new area of study: how gravity forces work in asteroid systems, where they aren't very strong. Although Dactyl is small relative to Ida's estimated 31-kilometer, 19-mile length, measuring around 1.4 kilometers, 0.87 miles, it nonetheless orbits steadily around its host. Suggested by the International Astronomical Union, its name suggests the fabled dactyls, creatures that helped the Greek deity Hephaestus in metallurgy. This name symbolically honors Dactyl's contribution to clarifying the complex physics of small body orbits and the mechanisms behind moon creation in hitherto unassuming solar system locations. How Dactyl came to be and how it got to circle Ida is one of the biggest puzzles about it. Asteroid crashes probably play a big role. Impacts can send pieces of debris into space, and some of that debris might stick together again if the conditions are right. In the case of Ida, a powerful impact a long time ago may have thrown off pieces that came together to form Dactyl. On the other hand, Dactyl could be a separate body that was caught by Ida's gravity during a close pass. But capture scenarios need very specific speeds and angles, which means that post-impact creation is more likely to be the case. The Galileo spacecraft's limited flyby data showed that Dactyl and Ida have similar spectral features, which suggests that they are made up of mostly silicate rocks. This fact supports the idea that Dactyl was made from Ida's own matter and not a stolen foreign body. Like Ida's, Dactyl's surface is full of small holes, which show that life can exist in a place full of waste, where micrometeorites regularly hit the surfaces of small objects in the solar system. Despite Dactyl's small size and the weak gravitational pull of both bodies, the Moon orbits Ida at a distance of only about 90 kilometers, 56 miles. In such a low-gravity scenario, even minor perturbations, like passing by another asteroid or experiencing subtle influences from Jupiter's gravity, could disrupt the orbit. Yet the fact that Dactyl remains bound suggests the system has managed to avoid strong external perturbations since its formation, surviving as a natural cosmic laboratory for gravitational interactions in miniature. Dactyl's discovery revolutionized how astronomers think about asteroids. Before 1993, most believed that asteroids were solitary chunks of rock drifting through the solar system. Today, satellites have been found around multiple asteroids and even binary asteroid systems where two roughly similar-sized bodies orbit each other are recognized as relatively common. Dactyl was the first piece of that puzzle, proving that complexity exists even in realms we once imagined to be simple. Practical lessons for future asteroid expeditions, especially those involving resource extraction or planetary defense, can be gained from studying Dactyl and Ida. How spacecraft may approach, land on, or reroute tiny bodies is informed by our understanding of their orbital stability. From a purely scientific perspective, as well as from the perspective of human aspirations for the potential future mining of asteroid resources, Dactyl's trailblazing position demonstrates how even the tiniest satellites may reveal astonishing details about the variety of our solar system. Cryovolcano chains of Pluto's Sputnik Planitia. Despite the fact that Pluto is far away and small, its surface is surprisingly complex and changing. There are signs of cryovolcanism all over its icy fields. Sputnik Planitia, a huge basin filled with nitrogen ice, is one of the most interesting places on Pluto. There are bands of cryovolcanoes all around this area that show Pluto's busy geological past and the processes that are still shaping its surface. Sputnik Planitia itself is a key player in Pluto's cryovolcanic activity. The smooth, glacier-like surface of this region is replenished by the upwelling of nitrogen ice, which flows outward to form the plains. At the basin's edges, cryovolcano chains rise like frozen sentinels, marking areas where subsurface reservoirs of volatile materials have erupted onto the surface. These cryovolcanoes, unlike traditional volcanoes, eject a mixture of water, ammonia, and methane ice rather than molten rock. Right Mons is one of the most impressive cryovolcanic features close to Sputnik Planitia. It is a huge dome-shaped feature that is 150 kilometers, 93 miles, across and rises 4 kilometers, 2.5 miles, above the nearby land. The shape of Right Mons looks like shield volcanoes on Earth. This is because it was made by repeated blasts of icy material. There is a big depression on top of Right Mons that might be a fallen crater. This is more evidence that it was formed by a volcano. Nearby, Picard Mons offers another example of Pluto's cryovolcanic activity. This towering structure reaches a height of 6 kilometers, 3.7 miles, making it one of the tallest features on Pluto's surface. Picard Mons shares similarities with Right Mons, including its dome-like shape and evidence of layered icy deposits. The proximity of these features to Sputnik Planitia suggests a shared source of subsurface material, possibly a liquid water or ammonia-rich reservoir beneath Pluto's crust. The cryovolcano chains around Sputnik Planitia are thought to be fueled by internal heat generated through radioactive decay in Pluto's rocky core. This heat, though modest, is sufficient to maintain pockets of liquid water or slushy mixtures beneath the Moon's icy shell. As these materials are forced upward by pressure or tectonic activity, they erupt onto the surface, creating the distinctive domes and flows observed near Sputnik Planitia. Cryovolcanic activity on Pluto is also influenced by its unique atmospheric and surface chemistry. The volatile ices that dominate Sputnik Planitia, nitrogen, methane, and carbon monoxide, are highly sensitive to temperature changes. These ices sublimate and recondense in response to seasonal variations, creating dynamic surface features and potentially triggering cryovolcanic eruptions. This interplay between Pluto's surface and atmosphere underscores the complexity of its cryovolcanic processes. The New Horizons spacecraft provided the first detailed images of Pluto's cryovolcano chains during its 2015 flyby. These images revealed the intricate textures and morphologies of Right Mons, Picard Mons, and the surrounding terrain, sparking new questions about the extent and timing of Pluto's cryovolcanic activity. The lack of significant cratering on these features suggests they are relatively young, possibly forming within the past few hundred million years. Galatea, Neptune, the shepherd moon. Galatea, a small moon of Neptune, is very important for keeping Neptune's Adam's ring in shape. The gravitational pull of Galatea, which is called a shepherd moon, helps keep the ring's particles together so they don't fly off into space. Galatea shows that even small stellar bodies can have a big effect on their surroundings, even though it is only about 180 kilometers, 112 miles, across. Shepherd moons like Galatea interact with their parent planet's rings through a process known as gravitational resonance. Galatea orbits just inside the Adam's ring, where its gravity creates narrow gaps and clumps in the ring's material. These interactions confine the particles within the ring and maintain its sharply defined edges. Without Galatea's influence, the Adams ring would likely spread out over time, becoming diffuse and less distinct. The surface and makeup of Galatea are still mostly unknown because no spaceship has taken a very clear picture of it. But Galatea is thought to be made up of a mix of water ice and rocks, just like Neptune's other inner moons. Its highly cratered surface shows that it has been hit by objects many times over a long period of time, and its irregular shape shows that it has not gone through major natural processes to become round. The way Galatea makes the ring's arcs is one of the most interesting things about her job as a guardian moon. These arcs are thick groups of matter inside the Adams ring that are grouped together in small areas instead of being spread out equally. The pull of Galatea's gravity helps keep these loops in place, but no one knows exactly how they formed. Figuring out how Galatea connects to the Adams ring could help us understand how similar things happen in other planetary systems, even those around other stars. Galatea's close orbit around Neptune exposes it to intense tidal forces, which may have shaped its interior and surface over time. These forces could cause internal heating, though not to the extent seen on larger moons like Europa or Enceladus. The effects of tidal stress are more likely to manifest in subtle surface features, such as fractures or slight variations in elevation. The finding of Galatea and the research that followed have shown how important small moons are in creating planetary systems. Galatea's link to the Adams ring was first found by observations from the Voyager 2 probe. Since then, observations from ground-based cameras have given us more information about how it interacts with Neptune's rings. These studies show how moons like Galatea can be used as nature labs to learn about how gravity works. Io, Jupiter, the volcanic powerhouse. Io, the innermost of Jupiter's Galilean moons, is the most volcanically active body in the solar system. Its landscape, shaped by more than 400 active volcanoes, is a dramatic showcase of relentless geological processes. This extreme activity is driven by tidal heating, a phenomenon caused by the gravitational interactions between Io, Jupiter, and neighboring moons Europa and Ganymede. These forces stretch and compress Io's interior, generating immense frictional heat that melts its mantle, creating vast underground magma reservoirs. The moon's volcanic activity was first observed by the Voyager spacecraft in 1979, revealing towering plumes of sulfur and molten rock rising hundreds of kilometers above its surface. Unlike Earth, where volcanoes are often associated with tectonic boundaries, Io's volcanoes are entirely powered by tidal forces. This constant flexing of Io's interior makes its volcanic energy output more than 25 times that of Earth's. Io's vibrant surface reflects its volcanic dynamism. Covered in yellows, oranges, reds, and blacks, its terrain is formed by sulfur and sulfur dioxide deposits, black lava flows, and bright frost from condensed sulfur dioxide. This kaleidoscope of colors underscores the moon's dramatic eruptions and intense geological activity. The moon's elliptical orbit amplifies these tidal forces, sustaining a constant cycle of heating and volcanic renewal. Loki Patera, the largest and most active lava lake in the solar system, is one of the most interesting volcanic features on Io. With a width of 200 kilometers, Loki Patera erupts on a regular basis, causing its crust to cool, harden, and flip over as new lava flows out of it. This process makes so much heat that it's more powerful than all of Earth's volcanoes put together. Loki Patera's eruptions also help make Io's atmosphere thin and the plasma torus that surrounds Jupiter. This shows how Io's volcanoes and its parent planet's magnetosphere are linked. Io's surface also reveals evidence of sulfur-based cryovolcanism. Bright, frost-covered regions around certain volcanic vents suggest eruptions of volatile sulfur compounds rather than molten rock. These deposits can stretch for hundreds of kilometers, forming smooth fields distinct from Io's rugged lava plains. Such cryovolcanic activity may result from pressure gradients in Io's sulfur dioxide-rich atmosphere, or from tidal heating pushing molten sulfur to the surface. Io's tall volcanic mountains make its geology even more interesting. These peaks, some of which are higher than Mount Everest, are not shield or composite volcanoes like most others. Instead, they are made up of huge chunks of rock that are being pushed up by strong geological forces. For example, Busal Montes rises about 17 kilometers above the fields around it, which shows how unstable Io's tectonic processes are. Io's mountains are mostly made up of silicate rock, which comes from lower layers of its crust being pushed upward by forces inside the planet. This is different from the plains, which are mostly sulfur. The Moon's unique subsurface structure further drives its extreme activity. Beneath Io's volatile surface lies a layered ocean of molten rock. Observations from the Galileo spacecraft reveal hotspots across the Moon, with temperatures exceeding 1,600 degrees Celsius, 2,900 degrees Fahrenheit. This subsurface magma interacts with Io's crust, creating networks of fissures that act as conduits for eruptions, delivering molten material to the surface in spectacular lava fountains and lakes. The layered nature of Io's magma ocean indicates varying viscosities and compositions, contributing to its complex volcanic behavior. The dynamics of Io's volcanic activity are further influenced by its neighboring moons. Gravitational interactions with Europa and Ganymede amplify tidal heating through orbital resonance, ensuring Io's elliptical orbit and sustaining its fiery heart. These interactions not only drive Io's eruptions, but also shape its chaotic surface. From its towering mountains and vast lava plains to its sulfur-rich cryovolcanism and subsurface magma ocean, Io represents a world of extremes. Its relentless volcanic activity is a testament to the power of tidal forces and the unique geological processes that define this remarkable moon. Europa's volcanic seas, Jupiter, a world of ice and fire. Europa is one of Jupiter's most mysterious moons. Its icy surface and the tantalizing possibility of an ocean below it fascinate both scientists and dreamers. This interesting moon isn't just a frozen sphere, it's also a living world where volcanic and cryovolcanic activity may change its surface and depths, suggesting that there may be life on other planets. Europa's surface is a bright, smooth expanse of ice, marked by dark streaks and ridges known as lineae. These features are believed to be fractures where subsurface water and slushy ice rise and refreeze, depositing materials from Europa's ocean. Such activity highlights the dynamic interplay between the Moon's surface and its subsurface environment, potentially driven by tidal forces and internal heat. Beneath Europa's icy crust lies a global ocean kept liquid by the heat generated through tidal forces exerted by Jupiter and its neighboring moons, Io and Ganymede. These immense gravitational interactions stretch and compress Europa's interior, creating frictional heat. At the ocean's floor, hydrothermal vents powered by volcanic activity may release heat and minerals, creating an environment akin to Earth's deep-sea ecosystems where life thrives in the absence of sunlight. Water mist clouds have been seen on Europa, which is proof of cryovolcanism. NASA's Hubble Space Telescope saw these plumes going hundreds of kilometers into space. They are caused by cracks in the ice. These kinds of geysers can hold water, salts, and biological molecules, which gives us a unique look into what the ocean is made of. Localized hotspots have also been found by the Galileo probe and later studies, which is more evidence of ongoing cryovolcanic processes. Europa's chaotic surface, characterized by ridges, dome-like structures, and regions of disrupted terrain, offers additional evidence of subsurface activity. These features likely result from warm ice or liquid water rising through the crust, driven by volcanic or hydrothermal heat. In some areas, the surface appears to have collapsed or been reshaped, indicating periods of significant internal activity. The effects of Europa's volcanoes are very serious. Aquathermal seeps on the ocean floor might be like places on Earth where living things depend on chemical energy instead of sunshine. These kinds of organisms, which are powered by volcanic heat, could help us figure out how life could start and stay alive in Europa's ocean. The larger Jovian system is also affected by cryovolcanism. The jets on Europa send out material that adds to Jupiter's magnetosphere, making a faint torus of charged particles. This exchange shows how Europa's activities are linked to those of its parent planet and affect life beyond its icy surface. The forthcoming Europa Clipper mission, set to launch in the 2020s, promises to revolutionize our understanding of this icy moon. By flying through plumes and mapping the surface with unprecedented precision, the spacecraft will analyze Europa's subsurface ocean and assess its potential habitability. Scientists hope to uncover biosignatures, chemical markers of life, within the plumes, providing direct evidence of life or prebiotic conditions. Callisto, dormant volcanism and the ice crust enigma. Geologically, Callisto, the farthest out of Jupiter's 4 main moons, is often thought of as a dead world. Heavy craters on its surface, which are very different from the active features of its neighbors Io, Europa, and Ganymede, show that it has been dormant and inactive for billions of years. But some scientists think that Callisto may have a more complicated natural history below its old layer of ice and rock. This past could include ancient or deeply buried volcanic activity. Unlike Io, Europa, or Ganymede, Callisto shows no direct signs of active volcanism or cryovolcanism. Its surface, pockmarked with craters, lacks the smooth plains and fissures associated with recent geological activity. However, Callisto's low density and the presence of water ice on its surface suggest that its crust may overlay a subsurface ocean or a layer of slushy ice. If true, this ocean could have influenced the Moon's geological past, potentially driving processes akin to cryovolcanism. The way Callisto's surface is shaped suggests that it may have had cryovolcanic action in the past. Callisto has some strange textures in some places, like bright streaks and hazy spots that look like they are on top of older craters. These features might be the remains of old cryovolcanic flows, in which water or a mixture of water and ammonia burst from the ground and froze when they hit the surface. Even though they weren't as exciting as Enceladus's geysers on Europa's plumes, these kinds of explosions would have helped bring parts of Callisto back to the surface. The gravitational forces exerted by Jupiter and the other Galilean moons may have also influenced Callisto's volcanic potential. While Callisto experiences much weaker tidal heating than its inner neighbors, even small amounts of heat could have driven localized melting within its icy crust. This melting could have created subsurface reservoirs of liquid water or slush that occasionally breach the surface through fractures, producing low-energy cryovolcanic eruptions. The density and magnetic field readings of Callisto give us more information about its internal structure, which helps us figure out how it might erupt as a volcano. People think that the Moon's center is divided into different levels. There is a rocky core inside the Moon, and around it are layers of ice and maybe even liquid water. This difference suggests that Callisto had a lot of internal warmth early in its past. This could have led to a time of cryovolcanic or volcanic activity before the Moon cooled down and stopped being active geologically. The way Callisto's possible volcanoes interact with Jupiter's atmosphere is one of the most interesting parts of the story. Because of its path, Callisto is in Jupiter's huge magnetic field. Charged particles hit its surface and create secondary magnetic effects. These interactions might heat up certain areas of Callisto's crust, maybe enough to cause random breakouts, or change how liquids behave below the surface. If Callisto's subsurface ocean exists, it raises the tantalizing possibility of habitability. While the Moon's lack of surface activity limits the chances of material exchange between the ocean and the surface, cryovolcanism could have served as a conduit in the distant past. Such exchanges might have introduced nutrients or energy sources into the ocean, creating conditions favorable for microbial life. NASA's Europa Clipper, or ESA's JUICE mission, may be able to help us figure out Callisto's natural past on future trips to the Jupiter system. Scientists can figure out if a volcano has been active in the past or is active now by looking at its magnetic field, surface makeup, and possible heat sources. Callisto is a great place for long-term study, including possible lander trips, because its surface is mostly clean and it is far from Jupiter's strong radiation. Enceladus, Saturn, cryovolcanic activity. The public and scientists alike have been enthralled by the remarkable cryovolcanic activity on the mid-sized moon Enceladus of Saturn. Cryovolcanoes on Enceladus, in contrast to more typical volcanoes, release organic-rich material, water and ice into space, proving, without a reasonable doubt, that the frozen moon has an ocean under its surface. Because of these explosions, Enceladus is now considered one of the best solar system locations to look for alien life. The discovery of Enceladus's cryovolcanism was made by NASA's Cassini spacecraft, which observed plumes of water vapor and ice particles erupting from fractures near the moon's south pole. These fractures, known as tiger stripes, are deep fissures that vent material from the ocean below. Cassini's flybys revealed that the plumes contain water vapor, salts, silica particles, and a variety of organic molecules, hinting at the ocean's potential habitability. Enceladus's cryovolcanic activity is driven by tidal heating, a process similar to the one powering Io's volcanism. As Enceladus orbits Saturn, gravitational interactions with the planet and neighboring moons create friction within its interior, generating heat. This heat prevents the subsurface ocean from freezing entirely and provides the energy needed to drive the plumes. The tiger stripes act as conduits, allowing material to escape from the ocean to the surface and into space. The composition of the plumes has provided key insights into the chemistry of Enceladus's ocean. Cassini detected salts, ammonia, methane, and molecular hydrogen, which suggest the presence of hydrothermal vents on the ocean floor. On Earth, such vents support diverse ecosystems, with microbes using chemical energy from the vents as a food source. The detection of molecular hydrogen on Enceladus suggests that similar processes could occur there, creating a potentially habitable environment. The cryovolcano activity of Enceladus is also important to Saturn's E-ring. Enceladus is an important part of Saturn's dynamic system because the ring is formed by material blasted from the plumes. Scientists have deduced information about the plumes and the interior of the moon from analyses of the E-ring. The potential habitability of Enceladus's ocean has made it a prime target for future exploration. Proposed missions, such as the Enceladus Life Finder, ELIF, or the Orbolander concept, aim to study the plumes in greater detail, searching for signs of life or prebiotic chemistry. These missions could sample the material ejected by the plumes without needing to land on the surface, providing a unique opportunity to study a potentially habitable environment directly. Enceladus's icy surface, bright and reflective due to its composition of water ice, contrasts with the dynamic activity occurring beneath. The presence of a subsurface ocean, hydrothermal activity, and organic molecules make Enceladus a model for studying icy worlds and their potential for supporting life. The Moon demonstrates that even in the cold outer reaches of the solar system, conditions for habitability can arise. The cryovolcanic activity of Enceladus has redefined our understanding of moons and their potential as habitats for life. Its plumes provide a window into the ocean below, offering invaluable data about the chemistry and dynamics of this hidden world. As we continue to study Enceladus, it serves as a beacon for future exploration and a reminder of the incredible diversity and potential of the solar system. Triton, Neptune, the cryovolcanic world. Triton, Neptune's biggest moon, is one of the most interesting objects in the solar system because it has cryovolcanism, which is a unique type of natural action. In contrast to normal volcanism, which is caused by melting rock, Triton's cryovolcanism is caused by nitrogen, ammonia, and water ice erupting. With its icy volcanoes, backwards rotation, and moving surface, Triton is a great example of how different planetary processes can be. The surface of Triton is a patchwork of smooth plains, rugged ridges, and chaotic, cantaloupe terrain. Voyager 2's 1989 flyby revealed a world constantly reshaped by geological processes. Cryovolcanic flows appear to have erased older impact craters, creating fresh and relatively young terrain. The cantaloupe terrain, characterized by rounded depressions, is thought to form through diaparism, where warmer, less dense material rises from Triton's interior, suggesting a constantly evolving core. Triton's cryovolcanic activity is fueled by internal heat generated through tidal interactions with Neptune. As a captured object from the Kuiper belt, Triton's retrograde orbit subjects it to extreme tidal stresses. These interactions heat subsurface layers, melting nitrogen ice and creating the pressure necessary for cryovolcanic eruptions. When this pressure builds to a critical point, nitrogen gas and icy particles are ejected through fractures in the surface, forming plumes that rise as high as 8 kilometers, 5 miles. Voyager 2 took pictures of Triton's plumes, which are some of its most interesting traits. These geysers get their power from both the sun and their own internal energy. They leave dark streaks of settled material on the surface. Nitrogen ice just below Triton's surface turns into gas when it gets warm from the sun. As the pressure builds up, powerful explosions happen that send nitrogen, water ice, and organic-rich particles floating around. There are a lot of different chemicals in these plumes, like methane and organic substances, which suggests that Triton's core is very complicated. Triton's cryovolcanism also plays a key role in shaping its surface. Smooth plains near the plumes may result from freshly deposited material, while dark streaks mark the fallout from eruptions. These features highlight the dynamic interaction between Triton's interior and surface, as well as its potential for harboring prebiotic chemistry. The mixture of nitrogen, water, and organics hints at the ingredients for life, raising the tantalizing possibility of chemical or even biological processes occurring beneath Triton's icy crust. The backwards motion of Triton and its exchanges with Neptune's tides have a big effect on its natural activity. These forces keep layers below the surface from freezing all the way through, so areas of liquid nitrogen and water stay. It is different from other icy moons because cryovolcanism on those moons is usually caused by radioactive warmth or interactions with other moons nearby. Triton is one of the most geologically active worlds in the outer solar system because of how hot its tides are. The study of Triton's cryovolcanism can help us learn more about icy volcanoes in other parts of the solar system. Scientists can make models of how cryovolcanism works in different types of environments by comparing Triton's behavior to that of moons like Europa and Enceladus. The Triton plumes are also a unique way to study how the surface of a moon interacts with its thin, nitrogen-rich atmosphere, since material from the plumes directly affects the atmosphere's makeup. Triton, like Neptune, is a mysterious moon that may be better understood in the future thanks to space probes. By analyzing plume composition, surface chemistry, and subsurface structures, advanced spacecraft fitted with spectrometers and imaging technologies might delve deeper into the cryovolcanic processes occurring on Triton. The possibility of prebiotic or life-supporting conditions on the moon's surface might be better understood with the help of such investigations. Titan, Saturn. Potential ice volcanoes. With its thick orange-tinged atmosphere, hydrocarbon lakes, and dramatic geological processes, Titan, Saturn's biggest moon, is a realm of stunning contrasts and secrets. Cryovolcanogenesis, in which ice rather than molten rock is expelled during volcanic eruptions, is one of the most fascinating features of Titan's geology. If Titan's cryovolcanoes are indeed active, we will learn a great deal about the gas giant's innards, atmospheric dynamics, and habitability. Cassini, NASA's probe, found surface characteristics that look like calderas, lobate flows, and volcanic domes, lending credence to the idea that Titan is a cryovolcanic formation. There is a deep depression around Sotra Patera that extends for more than 1,500 meters, 4,900 feet, and structures that resemble flows encircle it. This makes it a leading contender for a cryovolcano, standing at an elevation of almost 1,000 meters, 3,300 feet. Doom Mons is the peak that borders the caldera. These characteristics point to the possibility of ammonia or methane eruptions involving water ice, which may condense into a slushy substance that could flow across Titan's icy surface. Titan's cryovolcanic activity is likely fueled by internal heat generated by radiogenic decay in its rocky core and tidal interactions with Saturn. This heat could maintain subsurface reservoirs of liquid water or ammonia-rich mixtures. Periodic eruptions from these reservoirs might replenish Titan's methane-rich atmosphere, which would otherwise degrade due to photochemical reactions. Methane released by cryovolcanic eruptions could also influence Titan's unique weather system, driving processes like methane rain and river formation. The chemistry of Titan's cryovolcanic flows is particularly intriguing. Ammonia mixed with water lowers the freezing point, allowing the material to remain semi-liquid in Titan's sub-zero temperatures. This chemical environment could foster exotic reactions, potentially creating the precursors for life. The presence of organics in Titan's atmosphere and surface materials further adds to its astrobiological interest, positioning the Moon as a key target for the search for extraterrestrial life. Sotra Patera exemplifies Titan's cryovolcanic potential. The radar imagery from Cassini revealed flow-like structures radiating from its caldera, reminiscent of terrestrial lava flows, but composed of icy materials. These flows likely originated from subsurface reservoirs heated by internal processes, indicating that Titan's interior remains geologically active. Sotra Patera's activity could also play a significant role in maintaining Titan's atmospheric methane, a critical component of its dense haze and dynamic climate. Unfortunately, it is still hard to prove cryovolcanism on Titan because of the Moon's thick, cloudy atmosphere, which makes visible light studies harder. Cassini's radar and infrared tools gave us important information, but we need higher resolution readings to be sure that features like Sotra Patera came from cryovolcanic activity. Future projects, like NASA's Dragonfly rotorcraft, want to look at Titan's surface in more detail than ever before, studying its geology, makeup, and habitability potential. If cryovolcanism was found on Titan, it would have huge effects on the study of planets. It would show a moon that is not only busy geologically, but also able to keep a thick atmosphere and support complex chemical processes. If we can figure out how Titan's icy blasts happen, we might be able to figure out similar things that happen on other icy moons in the solar system as well. Ariel, Uranus, the hypothetical volcanic moon. Ariel is one of Uranus's bigger moons. It is a world of opposites, with features that point to a changing past shaped by geological and maybe even volcanic activity. Miranda's surface is more broken up, but Ariel's is mostly smooth, with some hills, dips, and craters here and there. These traits point to a past of resurfacing, which may have been caused by processes such as cryovolcanism. There isn't much clear proof that Ariel has had volcanic activity, but the structure of its surface and interior give us hints about what might have happened below its icy crust. Unlike its more fractured sibling Miranda, Ariel's surface exhibits smoother terrains interspersed with ridges, valleys, and craters. These features suggest a history of resurfacing, driven by processes that may have included cryovolcanism. While direct evidence of volcanic activity on Ariel is scarce, its surface and interior structure provide tantalizing clues about what may have occurred beneath its icy crust. Ariel's surface is composed primarily of water ice, mixed with smaller amounts of rock and organic compounds. This composition is typical of Uranian moons, but Ariel stands out for its relative brightness and fewer craters compared to its neighbors. The smoother regions of Ariel's surface indicate areas where older craters have been erased, suggesting that some form of resurfacing has occurred. This resurfacing could be the result of cryovolcanism, where water or other volatile materials erupted and flowed across the surface before freezing. The valleys and fault lines that run through Ariel are some of its most noticeable features. Some of them are hundreds of kilometers long. It is thought that these features formed when the inside of Ariel cooled and shrunk, which cracked the ice crust. It looks like some of these valleys are full of stuff that may have been put there by cryovolcanic flows. If this is true, these waves would have come from cracks or vents and spread out over the surface, covering up older land. The potential for cryovolcanism on Ariel is supported by its internal structure. Ariel's density suggests it is composed of roughly equal parts ice and rock with a layered interior. Heat generated by the decay of radioactive elements in the rocky core, combined with tidal interactions with Uranus and its other moons, could have created enough energy to melt subsurface ice. This internal heat might have driven the movement of liquid water or slushy mixtures to the surface, where they erupted as cryovolcanoes. Ariel's orbit around Uranus also plays a role in its geological history. As one of the innermost large moons, Ariel experiences tidal forces from Uranus that could generate heat through friction within its interior. These tidal forces are not as strong as those affecting moons like Io or Enceladus, but they may have been sufficient to sustain periods of internal activity during Ariel's early history. The evidence for Ariel's volcanic past remains indirect, as no spacecraft has provided detailed observations of its surface since the Voyager 2 flyby in 1986. Voyager's images revealed much of Ariel's surface, but lacked the resolution needed to confirm cryovolcanic features. Future missions equipped with advanced instruments could provide a closer look, identifying surface compositions and morphological details that would confirm or refute the presence of past volcanic activity. If cryovolcanism did happen on Ariel, it would probably change how people could live there. Liquid water or ammonia-rich mixes stored underground, even if only temporarily, could have made conditions good for prebiotic chemistry. There are smooth, resurfaced fields and filled valleys on Ariel that suggest it may have had periods of major geological activity. This would have changed the surface of the planet and could have affected its ability to support life. Proteus, Neptune, the almost spherical moon. One of Neptune's largest moons, Proteus, is a mysterious world that lies on the cusp between moons with an irregular form and those that are gravity-shaped into a sphere. Proteus may not have the flashy characteristics of other moons in Neptune's system, but it does offer a rare look at the subtle but important processes at work there. It is a key component of Neptune's intricate moon family due to its size, surface characteristics, and closeness to the planet. Proteus is irregularly shaped, with a diameter of about 420 kilometers, 260 miles, making it just barely too small for its gravity to pull it into a perfect sphere. Despite its irregularity, Proteus is the largest moon in the solar system that has not reached hydrostatic equilibrium, meaning it has not been shaped by its own gravity into a spherical form. This makes Proteus a unique object of study, offering insights into the structural limits of small celestial bodies. The surface of Proteus is heavily cratered, with its largest impact basin, Pharos crater, spanning about 230 kilometers, 140 miles, in diameter. This immense crater is close to the Moon's physical limits, as an impact of greater magnitude might have fractured or even destroyed Proteus entirely. The high density of craters suggests that Proteus is an ancient body, relatively untouched by resurfacing processes, and has remained geologically inactive for billions of years. Proteus is very close to Neptune and is just beyond the planet's faint ring system. Because they are so close, Proteus may help keep Neptune's rings in shape or change their structure. As it goes around, Proteus's gravity pull affects the particles in the rings, which could change how they are spread out and stop them from spreading even more. The composition of Proteus is thought to be a mixture of water ice and rock, similar to other moons in the outer solar system. Its dark surface reflects very little sunlight, giving it a low albedo that makes it challenging to observe from Earth. Voyager 2's 1989 flyby provided the most detailed images of Proteus to date, revealing its craters and irregular shape. but much about the Moon remains unknown. The history of Proteus is linked to the history of Neptune's moons. When Triton, Neptune's biggest moon, was captured, it probably messed up the positions of other moons, throwing some out of place and making others less stable. Proteus, which is in an orbit close to Neptune right now, may be a relic of this unstable time because it made it through the huge change in gravity that Triton caused. Proteus is an important part of Neptune's satellite system, even though it is small and doesn't have any physical action. It is a good candidate for further study because it interacts with the planet's rings and is in the middle of being an uneven moon and a spherical moon. By studying Proteus, we might learn more about how small moons are formed and how they connect with their parent worlds. Pan, Saturn, the ravioli moon. The name the ravioli moon comes from Pan, one of Saturn's strangest moons, which has a flattened shape and an equatorial ridge. As Pan orbits within Saturn's A-ring, it shapes the rings naturally by filling in a unique space called the Encke gap. Pan is an interesting thing to study because, despite being small, it has a big impact on the world around it. With a diameter of just 35 kilometers, 22 miles, Pan is one of the smallest moons in the solar system to exhibit such distinct morphological features. Its equatorial ridge, which gives it its ravioli-like appearance, is believed to have formed as material from Saturn's rings accumulated around the moon's equator. This ridge provides evidence of the dynamic interactions between moons and planetary rings, offering insights into how ring systems evolve. Pan's orbit places it within the Encke gap, a 325-kilometer wide, 200-mile wide region of Saturn's A-ring that it maintains through its gravitational influence. As Pan orbits, its gravity clears out particles in the gap, preventing them from reaccumulating. However, the moon's influence extends beyond simply creating a gap. It also creates waves and ripples in the edges of the A-ring, a phenomenon known as spiral density waves. These waves provide valuable data about the dynamics of Saturn's rings and the properties of the particles within them. Similar to other moons in Saturn's system, Pan is thought to be mostly made up of water ice. Its low density says that its structure is porous and that there is a lot of empty room inside it. The way it's put together and where it is in the rings suggests that Pan started out as a ring particle that slowly got bigger through aggregation. It has a unique shape and ridge that add to the evidence that it formed from stuff in Saturn's rings. Pan's discovery in 1990 was made using images from NASA's Voyager 2 spacecraft, but its details were revealed more clearly during the Cassini mission. High-resolution images from Cassini showed the moon's ravioli-like shape in remarkable detail, capturing the ridge and surface features that make Pan so distinctive. These observations have advanced our understanding of how small moons interact with their environments and contribute to the structure of planetary rings. Not only does Pan play a gravitational role, but its position inside the rings also makes one wonder about its stability in the long run. Over time, the moon's orbit might be affected by its interactions with ring particles and other surrounding moons, which could cause changes in its location or form. Modeling the development of Saturn's rings and the tiny moons trapped within them requires an understanding of these processes. Atlas, Saturn, the UFO-shaped moon. The remarkable similarity of Atlas, one of the innermost shepherd moons of Saturn, resembling a flying saucer, has captivated scientists. The moon's unusual form is mostly caused by its large equatorial ridge, which makes it look flatter in the middle. The impact that Atlas has inside Saturn's enormous ring system is substantial, despite its small size. Its mean diameter is just around 30 kilometers, or 19 miles. Atlas, one of numerous minor moons orbiting close to or inside Jupiter's rings, is extremely important in the formation of local ring material, particularly in keeping certain gaps and edges relatively small. Atlas orbits Saturn at the boundary of the A-ring, near the region known as the Roche division. Like its sibling moons Pan and Daphnis, Atlas is considered a shepherd moon because it exerts gravitational forces on surrounding ring particles. These forces can confine the ring particles, preventing them from spreading too far and preserving sharply defined ring boundaries. The Moon's gravity is not powerful by typical planetary standards, but it is enough to sculpt and maintain the features in Saturn's rings on the scale of tens or hundreds of kilometers, a feat made all the more impressive by Atlas's small size. Planetary experts are interested in how Atlas's unique equatorial ridge formed. One popular theory says that Atlas started out as a more spherical body, but as it orbited, it slowly picked up ring particles. Over time, these particles may have gathered along the Moon's equator, where its gravity pull and centrifugal force balance each other out. Eventually, they may have formed a clear line. The Moon's low mass and porous structure back this idea. This means that Atlas is mostly made up of water ice mixed with rocks. A high porosity would make it easier for extra ring material to stick, which would make the ridge stand out even more. NASA's Cassini spacecraft, during its mission in the Saturn system, 2004-2017, provided high-resolution images of Atlas, confirming its peculiar shape and surface properties. From these images, planetary geologists inferred that Atlas's surface is largely smooth and unblemished by deep craters, in stark contrast to many other small moons that are heavily cratered and irregular. The relative lack of craters suggests a younger surface, continually replenished by ring particles or minor collisions that redistribute and smooth out material. However, it might also reflect that Atlas's gentle gravity allows larger impacts to scatter debris into space rather than carve deep, lasting scars. Atlas's surface has some minor color changes that aren't related to its equatorial ridge. This might be because of how they interact with Saturn's atmosphere, or because different types of particles from the rings fall to Earth, like water ice versus darker, more biological dust. Atlas's surface is likely changed over time by a thin layer of ring material, making a mix of colors that looks like Saturn's other small ring moons, like Pan and Daphnis. Atlas shows how even small objects in space can have a big effect on their surroundings when it comes to Saturn's rings. Even though Atlas isn't as beautiful as Titan or Enceladus, its job as a guardian and its strange saucer-shaped shape make it an interesting object to study. It shows how delicate the gravity dance is that controls ring moon systems. A few small moons can keep the sharp edges of the rings, create temporary breaks, and keep the structure that makes Saturn's rings so beautiful to look at. Daphnis, Saturn, the wave-creating moon. The small moon, Daphnis of Saturn, is well known among astronomers for the spectacular waves it cuts into Saturn's rings. It is located in the tiny Keeler Gap, close to the outer border of Saturn's A-ring, and has a diameter of around 8 kilometers, 5 miles. Though dwarfish in comparison to other planets, Daphnis's gravitational pull is great enough to dramatically alter the Keeler Gap's periphery, creating waves and ripples that spread outward like a pebble dropped into a pond. These waves are generated by the subtle balance between Daphnis's gravity and the orbital velocity of the surrounding ring particles. As Daphnis orbits Saturn, completing a revolution in roughly 14 hours, it tugs gently on the icy particles that lie near the edges of the Keeler Gap. On the side closest to Daphnis, the particles move slightly toward the Moon's orbit. On the far side, they are nudged away from it. This differential pull causes the ring material to bunch and stretch, leaving behind distinctive vertical and radial waves that have been a hallmark of Cassini spacecraft images. While Daphnis's role is similar to those of its siblings Pan and Atlas, it differs due to its position within the Keeler Gap. There is a very small gap between the ring particles and the Moon's surface, only about 42 kilometers, 26 miles, wide. The gap is still safe, though, because of the Moon's shepherding action. The particles around Daphnis are held back by her gravity, so they don't spread too far across the ring plane. Daphnis is not perfectly round, according to high-resolution photos taken by NASA's Cassini spacecraft. Instead, it's long and thin, with a smooth surface that's somewhat dusty from ring particles. Its low density suggests that, like most of Saturn's inner shepherd moons, it is mostly water ice with a little amount of rock. Part of Daphnis's lack of deep craters is due to its mild gravity, which allows collision debris to readily scatter into space instead of leaving big scars. The vertical wave crests, often called wakes, can extend several kilometers above and below the main ring plane, illustrating the surprising three-dimensional structure of Saturn's rings in the vicinity of moon-induced disturbances. The interplay of Daphnis's orbit with local ring particles forms a constantly shifting pattern of peaks and troughs that move in sync with Daphnis's own progression around Saturn. These peaks are best observed during times of seasonal illumination changes, when the sun's angle accentuates vertical structures in the rings, allowing Cassini's cameras to capture shadows cast by these waves. The fact that it is very small, Daphnis is used by scientists to study planetary rings and the rules of orbital resonance. It shows how a single, tiny moon can keep gaps clearly defined and make big waves by pulling nearby ring particles together with its gravity. The stuff that makes up the ring, which could be anything from dust grains to things tens of centimeters across, has to follow Daphnis's careful rules for balance. In a wider sense, Daphnis stands for the fine complexity that supports Saturn's rings. Scientists are trying to figure out how rings form and change in our solar system and around other planets. Shepherd moons like Daphnis show us how even very small things can keep a sea of particles in order. Researchers learn more about the dynamical beauty of ring-moon systems by studying these interactions. Gravity and orbital mechanics work together to make the beautiful waves that Cassini's cameras record so clearly. It's not clear if Daphnis formed along with Saturn millions of years ago, or if it was just a stray chunk of ring material. However, its part in the Keeler gap shows how important even the smallest moons can be in shaping and protecting Saturn's beautiful ring structures. Volcanoes, hypothetical moons near Mercury. It is thought that the volcanoids are a group of small, asteroid-like objects that might go around the Sun inside Mercury's orbit. Volcanoids have not been proven to exist, but their presence is still a chance based on models of how they move. If these things exist, they would be the last area of safe orbits in the inner solar system that hasn't been examined yet. The volcanoids are named after the hypothetical planet Vulcan, which was once thought to orbit close to the Sun. Although Vulcan was disproven, the possibility of small rocky bodies in this region persists. Dynamical studies suggest that objects in stable orbits within Mercury's perihelion could survive for billions of years, shielded from gravitational perturbations by their proximity to the Sun. Because they are so far away, volcanoids are very hard to find. The area close to the Sun is bright and cloudy with solar glare, which makes it hard to make direct measurements. The best ways to look for these hard-to-find things are with cameras and coronagraphs that are in space. So far, no solid proof of volcanoids has been discovered, but the search goes on. New projects like NASA's Parker Solar Probe and ESA's Solar Orbiter are opening up new ways to learn more about this area. If volcanoids exist, they could provide valuable insights into the early solar system. These objects would likely be remnants of the protoplanetary disk that formed the planets, offering a snapshot of the conditions that shaped the inner solar system. Their composition, structure, and distribution could reveal details about the processes that governed planetary formation and migration. It's also important for world protection to look for volcanoids. Things in this area might be dangerous to flights going to Mercury, or very rarely to Earth. To evaluate these risks and come up with ways to lessen possible threats, it would be helpful to know their paths and physical features. Earth's second moon, the quasi-satellite Kamo'olalewa. Kamo'olalewa, a small near-Earth object, is sometimes referred to as Earth's second moon due to its quasi-satellite orbit. Unlike the Moon, which is gravitationally bound to Earth, Kamo'olalewa's orbit is primarily influenced by the Sun, with Earth acting as a secondary gravitational anchor. This unusual orbital relationship makes it a fascinating object for study, providing insights into the dynamics of near-Earth space. Kamaʻaolewa was discovered in 2016 by the Pan-STARRS 1 telescope in Hawaii. Its name, which means the oscillating celestial fragment in Hawaiian, reflects its peculiar orbital behavior. The object follows a complex path that appears to oscillate around Earth, but it is not gravitationally captured. Instead, its quasi-satellite status arises from a resonance with Earth, causing it to follow a similar trajectory as the planet around the Sun. Measuring about 40 to 100 meters, 130 to 330 feet in diameter, Kamaʻaolewa is a small object, making it challenging to observe and study. Spectral analysis suggests that it may be composed of silicate rock, similar to materials found in Earth's crust. This has led to speculation that Kamaʻaolewa could be a fragment of the Moon, possibly ejected by a past impact. However, its precise origin remains uncertain. Kamaʻaolewa's orbit is relatively stable, but it is not permanent. Simulations indicate that it has been in its current quasi-satellite state for about a century, and will remain in this configuration for several more centuries before drifting away. This transient nature adds to its uniqueness, as most near-Earth objects follow less complex trajectories. Kamaʻaolewa studies are very helpful for learning about how space near Earth changes over time. Because it is close, it could be the goal of future trips, such as sample return efforts. Finding out what it is made of and where it came from could help us understand how small things are formed and how they interact with planets. Knowing its path and features helps improve models of how near-Earth objects move, which makes it easier to predict when they might hit the Earth. As a small, easy-to-reach object, it can be used as a natural testing ground for tools that could be used to study or avoid dangerous asteroids. Venus, the volcanic enigma. Venus, often called Earth's twin due to its similar size and composition, is a planet shrouded in mystery and extreme contrasts. From its hypothesized lost moon to its volcanic-dominated landscape, Venus tells a complex story of catastrophic change, unique geological processes, and an atmosphere shaped by relentless volcanic outgassing. These mysteries hint at a tumultuous past and an environment radically different from Earth's. One weird thing about Venus that not many people know is that it may have had a moon in the past that we have lost track of. Venus doesn't have a natural satellite yet, unlike most of the other big planets. Because of this, some people think that a moon like Earth's moon might have formed billions of years ago after a big impact. In this case, the crash could have sent pieces flying into space that could have come together to form a moon circling Venus. The moon may not have lived long though, because Venus spins in a way called backward rotation, which is the opposite of its path. As we see with Earth's moon, the tides caused by this spin may have pulled the moon in instead of pushing it out. At some point, the moon might have gone past Venus's Roche limit, which is the key distance past which the tides would tear it apart. The pieces of this damage may have made a ring around Venus for a short time before falling back to the planet's surface. On the other hand, the moon may have been thrown into interplanetary space by gravity impacts with other planets or large objects in the early solar system. Pieces of this made-up moon could still be found as comets or meteorites, giving us fascinating but unproven clues about Venus's past. The absence of a moon has profound implications for Venus's development. Moons play a critical role in stabilizing a planet's axial tilt, which in turn affects climate and geological activity. Without a stabilizing moon, Venus may have experienced chaotic variations in its axial tilt, contributing to its extreme conditions today. These include a runaway greenhouse effect and a thick, toxic atmosphere dominated by carbon dioxide. Indirect evidence of this long-lost moon might be found by future Venus expeditions. Venus's impact basins or other geological characteristics associated with its development or destruction might be seen via high-resolution images of the surface. The cataclysmic events that formed Venus's early past may also be uncovered through isotope study of the planet's atmosphere. Venus's surface provides direct evidence of the planet's geological dynamism. Venus is a world dominated by volcanic features, with over 80% of its surface covered by volcanic plains, massive lava flows, and towering shield volcanoes. Mount Mons, the tallest volcano on Venus, rises 8 kilometers, 5 miles, above the surrounding plains, showcasing the immense heat and pressure driving Venusian volcanism. Unlike Earth, Venus lacks tectonic plate activity. Its stagnant lid tectonics mean that the crust behaves as a single, rigid layer. Heat trapped beneath the surface builds up over millions of years, eventually releasing through massive volcanic eruptions that flood large regions with lava. These eruptions drastically reshape the landscape, erasing older features and creating a young surface despite the planet's age. New evidence shows that Venus may still have volcanoes burning. Infrared hotspots and changes in the surface makeup that are consistent with ongoing eruptions have been seen by missions like NASA's Magellan and ESA's Venus Express. If this action is proven to be real, it would go against the long-held view that Venus is geologically dead. Volcanism is another important part of Venus's very cold atmosphere. Gases like sulfur dioxide and carbon dioxide are released by eruptions. These gases feed the dense atmosphere and make the greenhouse effect worse. Because of this process, Venus has become a dangerous world with 90 times higher air pressure than Earth and surface temperatures hot enough to melt lead. Unique volcanic features further highlight Venus's geological diversity. Pancake domes, formed from highly viscous lava, and arachnoids, spider-like surface patterns, demonstrate the variety of processes shaping the planet. These enigmatic formations offer glimpses into the interplay of volcanic and tectonic forces unique to Venus. New projects such as NASA's Veritas and Da Vinci Plus and ESA's Envision will try to solve the riddles of Venus, such as its lost moon and its active volcanoes. Advanced radar and spectroscopy will be used on these trips to make maps of the surface with never-before-seen levels of detail, study the makeup of the atmosphere, and look for signs of active volcanoes. Scientists want to learn more about Venus's history and how it became different from Earth by figuring out the processes that shaped its surface and atmosphere. The rogue moon of Saturn, Epimetheus and Janus's orbital dance. Two of Saturn's smaller moons, Janus and Epimetheus, have an orbital connection that is both unusual and mysterious. In a celestial phenomenon known as co-orbital moons, the distance between these moons and Saturn is as little as 50 kilometers, 31 miles. Astronomers have been captivated by their gravitational dance, which involves them switching orbits every 4 years. The two moons are similar in size and composition. Epimetheus measures about 116 kilometers, 72 miles across, while Janus is slightly larger, at 178 kilometers, 111 miles. Both moons are irregularly shaped and heavily cratered, composed primarily of water ice mixed with rocky material. Despite their physical similarities, it is their orbital behavior that sets them apart. Epimetheus and Janus occupy orbits just 151,000 kilometers, 94,000 miles, from Saturn's center, within the planet's diffuse E-ring. Their orbits are so close that they would collide if not for their unique gravitational interaction. Instead of crashing, the two moons exchange momentum when they approach each other. This exchange causes the inner moon to move to a slightly higher orbit, while the outer moon shifts to a slightly lower one, effectively swapping places. This delicate orbital dance repeats every 4 years, maintaining a stable system despite their close proximity. No one knows where this co-orbital interaction came from. According to one theory, Janus and Epimetheus were actually two halves of a bigger broken entity. After cooling to room temperature, the two moons reformed from the leftover pieces and found their present orbits. Two moons may have developed separately, but were drawn into resonance over time by gravitational interactions with Saturn or its moons. The orbital dynamics of Janus and Epimetheus provide valuable insights into gravitational interactions in planetary systems. Their ability to maintain stable orbits despite their proximity demonstrates the precision and complexity of celestial mechanics. These interactions also serve as a natural laboratory for studying co-orbital relationships, which could occur around other planets or even exoplanets. Janus and Epimetheus also influence Saturn's rings, particularly the E-ring. As they orbit, their gravity perturbs the ring's particles, creating faint gaps and waves. These effects, though subtle, contribute to the dynamic nature of Saturn's ring system and highlight the interconnectedness of the planet's moons and rings. Thanks to high-resolution photos and precise data on their orbits and surface characteristics, the Cassini spacecraft has considerably improved our understanding of Epimetheus and Janus. Thanks to these discoveries, we know more about how minor moons affect planetary systems and about co-orbital dynamics. Nix, Pluto, the tiny glittering moon. Nix, one of Pluto's smaller moons, is a tiny yet captivating member of the dwarf planet's complex satellite system. Discovered in 2005 alongside its sibling Hydra, Nix orbits Pluto in the company of its more famous companion, Charon, and two other small moons, Kerberos and Styx. Despite its diminutive size, Nix boasts unique features that make it a fascinating subject of study. Measuring approximately 50 kilometers, 31 miles across, Nix is irregularly shaped and has a highly reflective surface. Observations from NASA's New Horizons spacecraft in 2015 revealed that Nix's surface is covered in water ice, giving it a bright, glittering appearance. The moon's high albedo contrasts sharply with Pluto's darker regions, making it stand out despite its small size. The erratic spinning of Nix is one of its most interesting properties. As it circles Pluto, Nix bobs and weaves erratically, in contrast to the tidally locked moons of other planets. The interactions of Pluto's gravitational field with its moons, especially Charon, cause this erratic motion. The complicated gravitational environment that is created by these interactions destabilizes Nix's rotation, making it impossible to anticipate its orientation in space. Nix's irregular shape and chaotic rotation also raise questions about its origin. Like Pluto's other small moons, Nix is thought to have formed from debris created during a massive impact early in Pluto's history. This impact likely ejected material into orbit, where it coalesced into the current satellite system. Nix's composition and surface features provide clues about the nature of this primordial collision and the processes that shaped Pluto's moons. Finding and studying Nix has brought attention to the variety of minor moons in our solar system's outer regions. Nix may be a little object, but the things that make it tick provide light on how moons interact with their parent planets and how multi-moon systems work. It is an intriguing subject for more investigation due to its reflective surface, chaotic spin, and association with a spectacular impact event. In the future, trips to the Kuiper Belt might be able to get a better look at Nix and its neighbors, which would help scientists learn more about how they were formed and how they have changed over time. Such trips would also help us learn more about the processes that control small bodies in the outer solar system. This would help us understand the early past of the solar system and the forces that formed its current structure. Kerberos, Pluto, the hidden moon. Kerberos is one of Pluto's 5 known moons. It is a small, mysterious object that doesn't get as much attention as its bigger brothers, Charon and Nix. The Hubble Space Telescope found Kerberos in 2011. It is one of the least known objects in the Pluto system. Its small size, dim look, and strange features make it an interesting piece of the puzzle that is Pluto and its family of moons. Kerberos is remarkably small, with an estimated diameter of just 12 kilometers, 7.5 miles. Its size and low reflectivity make it difficult to observe, even with advanced telescopes. Unlike the bright, icy surfaces of other Pluto moons, Kerberos appears darker, suggesting a higher concentration of non-ice materials, such as rock or organic compounds, on its surface. This difference in composition raises questions about the moon's origin and its relationship with the rest of the Pluto system. Kerberos has a high mass-to-size ratio, which is one of the things that makes it so mysterious. Kerberos appears to have a higher density compared to Pluto's other minor moons, which are mostly made of water ice, according to observations. Scientists have speculated that Kerberos may have evolved differently or went through distinct processes that affected its density and composition because of this abnormality. Kerberos orbits Pluto in a nearly circular path between the orbits of Nix and Hydra, at a distance of approximately 58,000 kilometers, 36,000 miles. Like Pluto's other small moons, Kerberos is thought to have formed from debris created during a massive impact early in the dwarf planet's history. This collision likely ejected material into orbit, where it coalesced into the moons we see today. However, Kerberos's dark surface and higher density suggest that its formation or evolution may have been influenced by different factors. Like other minor moons in the Pluto system, Kerberos displays chaotic rotation. The complicated dynamical environment created by gravitational interactions with Pluto, Charon, and the other moons causes Kerberos to tumble unexpectedly as it circles. This erratic behavior exemplifies the difficulties of representing dynamics involving several moons, and represents the complex gravitational interaction present in the system. The New Horizons spacecraft provided the first close-up images of Kerberos during its flyby of Pluto in 2015. While these images revealed the moon's size and shape, they were not detailed enough to provide definitive answers about its surface features or composition. Future missions to the Kuiper Belt may offer more insights into Kerberos and its role in the Pluto system. Cressida, Uranus, the shifting moon. One of the smaller moons of Uranus, Cressida, is characterized by its unstable placement within the intricate satellite system of the planet. Uranus's inner family of moons, which are densely packed and gravitationally interwoven, includes Cressida, which was discovered in 1986 during the Voyager 2 encounter. With a diameter of about 79 kilometers, 49 miles, this tiny moon with an unusual shape provides a rare look at the intricate gravitational ballet performed by Uranus's moons. The future of Cressida remains uncertain, which is one of the things that makes it so interesting. Cressida is now on a course that might lead to a collision with one of the neighboring moons, Desdemona in particular, due to gravitational interactions. Because of how near these moons orbit, computer models indicate that collisions will occur within a few million years. Debris from such a collision may either combine with other bodies or create a new ring around Uranus. Cressida's composition is thought to be primarily water ice, with small amounts of darker material, giving it a low albedo similar to other inner Uranian moons. This low reflectivity makes it challenging to observe from Earth, but it also suggests that the moon's surface has been darkened over time by radiation and micrometeoroid impacts. The lack of geological features on its surface indicates that Cressida is geologically inactive, preserving an ancient record of impacts and space weathering. The gravitational interactions among Uranus's inner moons create a dynamic environment where small changes in one moon's orbit can ripple through the system. Cressida's interactions with nearby moons, including Desdemona and Juliet, result in orbital resonances that subtly alter their paths over time. These resonances contribute to the long-term instability of the system, making it one of the most tightly packed and precarious moon systems in the solar system. Cressida's orbit lies within Uranus's faint epsilon ring, and the moon's gravity likely influences the ring's structure. By confining particles within the ring, Cressida plays a role similar to that of Saturn's shepherd moons, shaping and maintaining the ring's sharp edges. These interactions highlight the interconnectedness of moons and rings in planetary systems. Cressida is a significant target for future investigation, despite its little size and dim appearance. Gaining a better grasp of how it interacts with the moons and rings of Uranus might shed light on the inner workings of systems of closely packed moons and the factors that cause orbital instability. The surface and composition of Cressida can also be studied to learn more about the history and development of the moons of Uranus. The universe is a treasure trove of mysteries, and its moons are no exception. As we continue to explore these forgotten worlds, each discovery deepens our understanding of the cosmos and our place within it. What other fascinating moons do you think deserve the spotlight? Comment below, and if you enjoyed this journey through the solar system's forgotten companions, don't forget to like, subscribe, and hit the notification bell for more cosmic explorations. Thanks for watching.